Welcome everybody to your all-in-one machine learning from scratch video. This video takes all 15 parts of my ML from scratch series and combines it into one single video. In this series we are going to implement the most popular machine learning algorithms using only pure Python and NumPy. This is perfect if you are at a beginner or intermediate skill level and want to get a deeper understanding how all these algorithms work. All videos also contain a little theory section before we jump to the code. I will leave timestamps for each section, and of course all the code is available on GitHub. I also created a free NumPy handbook that covers all the essential functions that you have to know in NumPy, and it contains useful code examples for all sections. So you can download this ebook for free on my website. I will leave the link in the description. So let's get started, and if you enjoy this content, be sure to leave me a like and consider subscribing to the channel. Hi everybody, welcome to a new tutorial. This is the first video of a new series called Machine Learning from Scratch. In this series we are going to implement popular machine learning algorithms using only built-in Python modules and NumPy. So today we will start with the k-nearest neighbor algorithm, or short KNN algorithm. The concept of KNN is fairly easy. A sample is classified by a popularity vote of its nearest neighbors. So let's consider an example with two classes and a two-dimensional feature vector. So let's have a look at this figure. So here we have two classes, the blue class and the orange class. And we have feature vectors with two dimensions. So we have x1 on this axis and x2 on this axis. And what we do here is we have some training samples, and then for each new sample that we want to classify, we calculate the distance of this sample to each of the training samples, and then we have a look at the nearest neighbors. So in this case we have a look at the three nearest neighbors, so these ones. And then we choose or predict the label based on the most common class labels here. So we have two blue classes and one orange class. So this then will be a blue class. And this is the whole concept of the KNN. And what we also have to know is, in order to calculate the distances, we use the Euclidean distance. So in a 2D example, the Euclidean distance of 2 points is defined as the square root over, and then we have for each feature vector component, we have the squared difference. So we have x2 minus x1 squared plus y2 minus y1 squared. So this is the Euclidean distance in a 2D case, and in a more general case the formula is defined as this. So it's the square root over the sum from I equals 0 to n, where n is the number of dimensions, and then we have the sum over each component, and for each component we calculate the squared distance or the squared difference. So this is the Euclidean distance, and this is all we have to know in order to implement the KNN. So let's start, and first let's define a class called KNN, and this has of course an init method. So init self, and this will get a k. So this is the number of nearest neighbors we want to consider, and this will also get a default value. So the default is 3. And in the init, we define the init. So in the init we simply want to store the k, so we say self.k equals k. And then what we want to implement here, and here we want to follow the conventions of other machine learning libraries, for example the scikit-learn library. So we have a fit method. So this will fit the training samples and some training labels, and this will usually involve the training step. So we want to implement this one, and then we also want to implement a predict method. Sorry, this also has self. And the predict method, so here we want to predict new samples. So these are the methods we want to implement. And now, before we go on, first of all, let's have a look at how our data looks. So what is this x and this y? And for this I wrote some test script. So here I used the famous iris data set. So you might have heard about this already. So I can get this from the scikit-learn module. And then I will generate some training samples and some test samples and the associated training labels and test labels. So let's first have a look at how this training samples look. So we want to print the shape of this one. So this is a NumPy ND array of shape 120 by 4. So 120 is the number of samples and 4 is the number of features for each sample. So for example, let's print the first sample. So this is 4 features in it. So this is how our training samples look. And now let's have a look at our training labels. So this is a 1D row vector, also of size 120. So for each of our training samples, we have the label for it. So if we print this, then we see this will be a 1D vector with only one row. And now what we see here is we have labels 0, 1, and 2. So this is a 3-class problem. So let's also plot this. And now, for example, what I plot here is I only plot the first 2 features, so that we have a 2D case. So this is how our data looks. So we have 3 classes, red, green, and blue. And yeah, so this is how our data looks. And now we can continue by implementing this. So in our fit method, so in the KNN algorithm, this doesn't involve a training step. So what we do here is we simply want to store our training samples and then we can use them later. So we can say, so let's store them. So let's say self, and then we call this x train equals x, and self y train equals y. So this is all for our fit method. And now for our predict method. So this will can get multiple samples here. So we can see this because we use a capital X for this. So this can have multiple samples. So we can write a little helper method. So we want to do this for each of the samples. We want to say we want to get the predicted labels equals, and then we write a helper method that we call underscore predict, and this will only get one sample. So here we use list comprehension. So what we want to do then is we want to call this self predict with one sample x, and then we want to do this for all of our samples in our tests samples here, so for small x in capital X, and then this will be a list. So let's convert this to a NumPy array, and then this is our predict method, and of course we have to import NumPy, so we say import NumPy as NP. And now how does our underscore predict method look like? So now again, let's have a look at the figure here. So what we do is we want to calculate all the distances, and then we have a look at the nearest neighbors and the labels of the nearest neighbors, and then we do a majority vote and choose the most common class label. So let's write some comments here. So first of all, we want to compute the distances. Then we want to get the k nearest neighbors, so get k nearest samples, and we want to get the labels, and then we do a majority vote, so we want to get the most common class label. So let's do this. So let's say distances equals, and now as I said, we use the Euclidean distance here, so let's define this. And we want to define this as a global function, so you might want to write this in a separate file or call this in some utility class. So here I will simply do it in the same file, so I say Euclidean distance of two feature vectors, so let's say x1 and x2. And now again, let's have a look at the formula. So this is the square root and then the sum over each squared distance. So we have the square root, so we can say NumPy dot sqrt, and then we have the sum, so we can use NumPy dot sum. So this will calculate the sum for over each feature vector component, and here we have the squared difference, so we can say x1 minus x2 to the power of 2. So this is all we need, and then we want to return this, of course. And now in our predict method, what we want to do is we want to calculate the distances of this one new sample to all the training samples. So we also use list comprehensions here, and we call this Euclidean distance with our new test sample. So, and then to each of the training samples, so we say small x train, and then we want to calculate this for x train in capital or in self dot x train. So now we have all the distances, and now we want to get the k nearest samples and the labels. So what we do here is we sort our distances, and we can do this. So let's call this the k indices, and here we use NumPy argsort. So this will sort the distances and will return the indices of how this is sorted. So here we call distances, and this will be an array, and we only want to have the k closest samples. So let's use slicing here, and let's start at the beginning, so 0, or we can omit this, and this goes only until self.k. So this will be the indices of the k nearest samples. And now let's get the labels. So we get the k nearest labels equals, and here we also use list comprehensions, and then we get the label of each training labels with this index. So the index I, and then for I in k indices. So now we have the labels of our nearest neighbors, and then we use a majority vote and get the most common class label. So let's call this most common equals, and for this we use another Python module. So we use the counter module. So we say from collections import counter, and then we get a counter of the k nearest labels, and then this is a method called most common, and we only want to have the first or the very most common. And now let's have a look how this looks. So if I comment this out, and let's write a short example what the collections or the counter module will do. So let's say we have a list A equals, and this is some values in it, so 1 1 1 2 2, and then some other labels. So also from collections import counter, and now we get the most common equals. So we create a counter of this list and then one most common. So let's print this. So I have to close this first, so let's run this again. So this will be a list, and then we have a tuple of the most common items. So for example, if in this case we want to have the one most common item, and this is a tuple, and the first item here is the most common item, so this is 1, and the second item is the number of times this is in our list, so 3 times 1. So for example, if you use 2, then it will also put in the second most common items. In this case it is 2, and we have 2 times 2. So we only want one most common. So as I said, this is a list. So in order to get the first item, we use the index 0. So now we have the tuple, and now to get the actual items, again we use the first index, and then we have 1. So here we have to do the same thing, and we want to return this. So let's return most common of index 0 of index 0. And this is all our implementation of the KNN algorithm. So let's try this out. So let's, in our test example, we already have our test file, we already have our training and test samples. So let's use our KNN class. So we can say from KNN import KNN and then create a classifier. So CLF equals KNN. And so let's use k equals 3. And then we want to call the fit method first. So we want to fit our X train and the Y train. And then we get the predictions. And this is we do this by calling clf.predict, and then we want to predict our test samples, so x test. And now let's calculate the accuracy. So accuracy, so this is defined by how many of our predictions are correctly classified. So this is so here we use the sum. And here we write predictions equals y test. So for each prediction that is the right or the same as the correct label, it adds 1, and then we divide this by the number of test samples. So we divide this by lang y test, and let's print our accuracy and see if this works. So yeah, in this case it's 1.0, so all of our predictions are correct. So let's use another number of neighbors. So k equals 5. So usually you want to use an odd number here. So let's run this. Oh, sorry. So in this case it's 0.96. So not as good as with 3 neighbors, but also very good. And yeah, we see that this is working, and this is our whole implementation of the KNN. And yeah, I hope you enjoyed this tutorial, and see you in the next tutorial. Bye. Hi everybody, welcome to a new tutorial. This is the second video of the Machine Learning from Scratch tutorial series. In this series, we are going to implement popular machine learning algorithms using only built-in Python modules and NumPy. Today we are going to implement the linear regression algorithm. So let's talk about the concept of linear regression first. So in regression, we want to predict continuous values, whereas in classification, we want to predict a discrete value, like a class label 0 or 1. So if we have a look at this example plot, then we have our data, the blue dots, and we want to approximate this data with a linear function. That's why it's called linear regression. So we use a linear function to predict the values. So we can define the approximation as y hat equals w times x plus b. So this is a line equation where w, or our weights, is the slope and b is the bias, or just the shift along the y-axis in the 2D case. So this is the approximation, and now we have to come up with this w and the b. And how do we find this? So for this we define a cost function, and in linear regression this is the mean squared error. So this is the difference between the actual value and the approximated value. So the actual value, for this we need training samples, and then we square this difference and sum over all the samples and then divide by the number of samples. So this way we get the mean error. This is the cost function of the, so this is the error, and of course we want to have the error as small as possible. So we have to find the minimum of this function. And how do we find the minimum? So for this we need to calculate the derivative or the gradient. So we calculate the gradient of our cost function with respect to w and with respect to b. So this is the formula of the gradient. Please check this for yourself, and I will also put some links in the description with some further readings, but I will not go into detail now. And now with this gradient, we use a technique that is called gradient descent. So this is an iterative method to get to the minimum. So if we have our object or our cost function here, then we start somewhere. So we have some initialization of the weights and the bias. And then we want to go into the direction of the steepest descent. And the steepest descent is also the gradient. So we want to go into the direction of into the negative direction of the gradient. And we do this iteratively until we finally reach the minimum. And with each iteration, we have a update rule for the new weights and new bias. So the new W is the old W minus alpha times the derivative. So minus because we want to go into the negative direction. And then this alpha is the so-called learning rate. And this is an important parameter for our model. So the learning rate defines how far we go into this direction with each iteration step. So for example, if we use a small learning rate, then it may take longer, but it can finally reach the minimum. And if we use a big learning rate, then it might be faster, but it might also jump around like this and never find the minimum. So this is an important parameter that we have to specify, and please keep that in mind. So now that we know our update rules, I've written the formulas for the derivatives again here, and then simplified them a little bit. Please check that for yourself. So these are the formulas for the update rules and the derivatives, and this is all we need to know. So now we can get started. So now let's define a class called Linear Regression, and this will of course has an init method or double underscore init, and then it has self, and it gets the learning rate, and I will give this a default value. So usually this is a very small value, so I will give it 0.001, and then I will give it a number of iterations, so how many iterations we use in our gradient descent method, and I will also give this a default value, so I will say this is 1000. And then I will simply store them here. So I will say self LR equals LR, and self n iters equals n iters. And then later we have to come up with the weights. But here at the beginning I will simply say self weights equals none, and self.bias equals none. And then we have to define two functions, and we will follow the conventions of other machine learning libraries here. So we will define a fit method, which takes the training samples and the labels for them. So this will involve the training step and the gradient descent. And then we will define a predict method. So then when it gets new test samples, then it can approximate the value and return the value. So these are the functions we have to implement. And before we go on, let's have a quick look at the data x and y. So how does this look? And for this I've written a little example script, and I used the scikit-learn module to generate some example data, and I will split the data into training and test samples and also training and test labels. So first of all, let's have a look at how this data looks. So here is the plot. So this is how our data looks, and now we want to find a function somewhere here that approximates the value. And let's have a look at the shape of our x and y. So let's run this, and no, I don't want this plot here anymore. So if we see that our x is a ND array of size 80 by 1, and this is because I put in here I want to have 100 samples and one feature for each sample, and then I will split this so our training samples only has 80 samples in it. So this is a ND array of size 80 by 1, and our training labels is just a 1D row vector of also of size 80. So for each training sample we have one value. So this is how our data looks, and now let's continue. So let's implement the fit method. So as I said, we need to implement the gradient descent method here, and the gradient descent always needs to start somewhere. So we need to have some initialization. So let's init our parameters, and for this first let's get the number of samples and the number of features. And we can get this by saying this is x.shape, and then we simply initialize all the weights with 0. So we can say self weights equals NumPy zeros of size and features. So for each component we put in a 0, and self.bias equals 0. This is just a value. So you can also use random values here, but 0 is just fine. So let's use 0 here, and then we use the gradient descent. So this is an iterative process, so we use a for loop. So for I, or actually we don't need this, so for underscore in range, and then self.niters. And now what we need, we first have to approximate, or let's have a look at the formula again. So the formula for our new weights is the old weight minus the learning rate times the derivative, and the derivative with respect to w is 1 over n, and then we have the sum, and the sum over 2 times xi times, and then the difference here of this approximated and the actual values. So let's first calculate this approximation. So we have this formula here. The approximation is the weights times our x plus the bias. So let's do this. Let's say, and let's call this y predicted equals, and then we can use np dot and then x and self.weights plus bias. So this will multiply the x with the weights, And now that we have the approximation, we can calculate the derivative with respect to w. And this is, let's again have a look at this formula, 1 over n, and then the sum, and then inside the sum we have the product of x times this. So we say 1 over n samples, so we already got the number of samples here, and then times, and then we have the sum product, so this is nothing else but also the dot product, so np dot dot. But now we have to be careful. So what we did here, here we multiply each weight component with the feature vector component and sum it up. And we do this for all samples and then get one value for each sample. And here we want to get one value for each feature vector component. So we multiply each sample with the predicted value and sum it up. So, and then we do this for each feature vector component and get one value for each component. So this is the other way around. So this is along the other axis. And we can, so we have to use x dot transposed here, x dot t. And this is the dot product of the transposed x, and then we have y predicted minus the actual y. So please check the NumPy dot function for yourself. So this is the derivative of the w, and the derivative of the bias is also 1, or again, let's have a look at the formula. So this is the same, except that we don't have the x here. So this is 1 over n, and then just the sum of this difference. And by the way, I left the 2 out, so this is just a scaling factor that we can omit. So here 1 over n, and then the sum over the difference. So again, 1 over number of samples, and then we can say numpy.sum, and the sum of y predicted minus actual y. So these are our derivatives, and now we update our weights. So we say self weights minus equals self dot learning rate times this derivative, and self dot bias equals self minus equals self dot learning rate times the derivative. And yeah, so this is the gradient descent, and now we need the predict method. So again, we approximate the values with this formula. So we already have this here. So this is the dot product of x and the weights plus the bias. And then we simply return this. So this is the whole implementation that we need, and I forgot to import NumPy, of course. So I say, let's say import NumPy s and p so that we can use this. And now let's test this. So let's import this class. So let's say from Linear Regression, import Linear Regression, and then create some regressor equals Linear Regression, and then we say regressor.fit, and we want to fit the training samples and the training labels. And then we can say we can get predicted values equals regressor dot predict, and now we want to predict the test samples. And now in order to calculate or to see how our model performs, now we can't use the accuracy measure, but here we use the mean squared error. So as I said, this is our cost function, the mean squared error, that tells us how big the difference between the actual value and the approximated value is. So let's define the mean squared error. Let's say def MSE, and this will get the actual values and the predicted values. And this is the NumPy. Here we can use NumPy mean, and then simply the difference to the power of 2, so y true minus y predicted to the power of 2, and then we want to return this. So let's see, or let's say MSE value equals MSE of y test and the predicted values, and let's print this. So now if we run this, see, it's not running, bias is not defined. So let's say what did we miss here, self.bias, and let's run this again. So line 27. Oh, sorry, I copied this and forgot this here too. So next try. Now we see that our performance, so the mean squared error is 783, so this is pretty high. So let's use another learning rate here. So let's say LR equals 0.01, and let's run this. And now we see that our error is smaller, and let's actually plot this. So let's plot first with the original learning rate. Let's see how the plot looks. So now our plot looks like this. So it's almost like the right slope, but not exactly. And now let's have the other learning rate. So let's use this learning rate and let's run this. And now our plot looks like this, and this looks pretty good actually. So this is a pretty good fit or pretty good approximation of this data with a linear function. So we see that our implementation is working, and I hope you enjoyed this tutorial, and see you in the next tutorial. Bye. Hi everybody, welcome to a new machine learning from scratch tutorial. Today we are going to implement logistic regression using only built-in Python modules and NumPy. If you haven't watched my previous video about linear regression, I will highly recommend to watch it first, since I explain some of the concepts a little bit more in detail there. But I will try to cover all the important concepts again in this video. So let's talk about the concepts of logistic regression. So as you remember, in linear regression, we model our data with a linear function, w times x plus b. So this will output continuous values. And now in logistic regression, we don't want continuous values, but we want a probability. And in order to model this probability, we apply the sigmoid function to our linear model. So the sigmoid function is 1 over 1 plus the exponential function of minus x. So this is the sigmoid function, and x in our case is then our linear model. So, and this will output a probability between 0 and 1. So if we plot the sigmoid function, then you can see this is between 0 and 1. So with this function we can model a probability of our data. And now with this approximated output, we must then come up with the parameters W, so our weight and our bias. And how do we do that? So again, I already explained this in the previous video. So we apply a method that is called gradient descent. So first of all, we need a cost function. And here we don't have the mean squared error anymore, but we use a function that is called the cross entropy. So this is the formula. I will not go into detail about this, but I will put some further readings in the description. So with this formula, what we do, we want to optimize this with respect to our parameters W and B. So we use gradient descent, and this means we start at some point and then iteratively update our parameters. So we have to calculate the derivative and then go into the direction of this derivative until we finally reach the minimum. So, and then we also need to define a so-called learning rate. So the learning rate determines how far we go into this direction with each step. So this is an important parameter. It shouldn't be too high, since then it might jump around and never find the minimum, but it also shouldn't be too low. Sorry. And now with this gradient descent, what we have is we have our update rules. So our weight is, our new weight is the old weight minus, because we want to go into the negative direction, minus our learning rate times the derivative. And the same is for our bias. And then here are the formulas that we need for our derivatives. So these are the formulas, and they are actually the same derivatives like in linear regression. So you can check the math behind it yourself. I will also put some links in the description. And this is all we need now to get started. And now we can implement our logistic regression. So of course we use NumPy again. So let's import NumPy as NP. And then we create a class called Logistic Regression. And this will have an init method. So we have an init. And the init looks exactly the same as for linear regression. So I will put some learning rate in here that will get a default value, so 0.001. Usually the learning rate is very small. And it will also get a number of iterations, so n iters, and with a default of 1000. So this will determine how many iterations we use for our gradient descent, and then I will store them. So I will say self LR equals LR and self n iters equals n iters. And then I will simply create some weights, but set them to none at first. So our weights are none and our bias is none. Simply that we know now we need to come up with them. And then we define a fit method. So here we follow the conventions of the scikit-learn library again. So this will take some training samples and the values, the training labels. So this will involve the training step and the gradient descent. And then we have a predict method. And here we get new test samples that we want to predict. So these are the methods we want to implement. And our inputs here, so x is a NumPy ND vector of size m times n, where m is the number of samples and n is the number of features for each sample. And y is a 1D row vector, also of size m. So for each training sample we have one vector. So now we can go on. So first of all, we have to initialize our weights. So let's say we want to init the parameters. And for this we get the number of samples and the number of features. So this is x shape. So this will unpack the shape, the first dimension into the number of samples and the second dimension into the number of features. And then we init our weights just with zeros. So we create a vector only with zeros of size, number of features. And we set our bias to 0 at first. You can also, for example, use random numbers for the initialization, but 0 is just fine. And after that, we use the gradient descent that I talked about. So we iteratively update our weights. So we use a for loop. So let's say for I. And actually we don't need this, so for underscore in range and then self dot and iters. So this is the number of iterations we want to have. And now let's have a look at the formula again. So first of all, we approximate our y with this function. So first let's apply this linear model and then apply the sigmoid function. So let's say linear model equals, this is w times x plus b. So we can use the NumPy dot function to multiply our vectors. So multiply x and self dot weights plus self dot bias, and then we apply the sigmoid function. So let's create some helper method, some private method sigmoid that gets some x. So and here this is just, if you have a look at the formula, 1 over 1 plus the exponential function of minus x. So we can write this in one line, 1 return 1 over 1 plus np dot, or let's make parentheses around this, 1 plus np dot exp, and then of minus x. And then this is all we need. So now we apply the sigmoid function here. So we say y predicted equals self dot sigmoid of, and then our linear model. So this is our approximation of y. And then we need to update our weights. So if we have a look at the update rules, we first calculate the derivatives with these two formulas. So let's say dw equals, and this is 1 over n, and then the sum of 2 times x times the difference of the predicted y minus the actual y. So we have 1 over the number of samples that we already got up here, and then times, and then we have the product, and then the sum over this product, and this is nothing else but also the dot product of vectors. So we can use NumPy dot, but now we have to be careful. Now we want to do this along the other dimension, so we have to use x dot transposed, and then the dot product of this and y predicted minus the actual y. So please check the dot product for yourself. So this is the derivative with respect to w, and the derivative with respect to the bias is the same, but only without the x. So this is just a sum. And by the way, I left the 2 out because this is just a scaling factor that we can omit. So this is 1 over n, and then the sum of this difference. So we say dB equals 1 over number of samples, and then times np dot sum, and then here we simply have y predicted minus the actual y. So these are our derivatives, and then we update our our parameters. So we say self.weights minus equals self.learning rate times the derivative, and the same for our bias. So minus equals self.learning rate times the derivative. And this is all for our fit method. This is the gradient descent. And now let's implement the predict method. So here we do the same thing that we did here. So we first approximate our data with a linear model, and then apply the sigmoid function to get a probability. And now what we want is we want to say if it's either class 1 or class 0. So we look at this function and we say if it's larger than 0.5, then it's class 1, and if it's lower, then it's class 0. So let's say our y predicted class or classes, this is for multiple samples, equals, and then we use list comprehension, and we say it's 1 if our I is larger than 0.5, and otherwise it's, or else it's 0. And then we do this for each y, for each probability in our y predicted. So now we have 0 or 1s, and then we just return this. So return the predicted classes, and this is the whole implementation that we need. And now we can test it. So I already wrote a little test script where I used the scikit-learn modules to load some test data. So this is the breast cancer set. You can Google that. So this is a popular 2-class problem. And then I will split the data into training samples and test samples. Then I will create some logistic regression model with from our file that we and our class that we just implemented here. And then I will fit the data, our training data and the training labels, and then I will predict this and predict the labels for the test data, and then I calculate the accuracy, so how many of the labels are correctly assigned. So if you've watched the video about the KNN algorithm, then you already have seen this. And now let's run this. So here got an unexpected keyword argument, learning rate. Oh, sorry. I just called this LR. And this is the number of iterations. So let's run this again. And then we see our accuracy is 0.92, so or almost 93% of our test data is correctly assigned. So we see that it works, and I hope you enjoyed this tutorial, and see you in the next tutorial. Bye. Hi everybody, welcome to a new Python tutorial. So in this video I will simply refactor the code of the last two videos. So if you haven't watched the previous two videos about linear regression and logistic regression, then please do so. So now if you compare the code, then you will see that it's almost similar. So both classes have exactly the same init method, and both have almost the same fit method. So in both classes we init our parameters, and then we do the same gradient descent, except that in the linear regression we have simply this linear model for our approximated y, and in logistic regression we also have this linear model, but then we also apply the sigmoid function, and this same difference is in the predict method. So in linear regression we simply apply the linear model, and in logistic regression we apply the linear model and then the sigmoid function, and then say if it's 1 or 0. And we have this helper function, but a lot of this code is similar. So let's refactor this, and let's create a base class and call it base regression. And our two classes will be derived from this base regression. So let's say linear regression derived from base regression, and the same for our logistic regression. And then we can cut the init method and put it in the base regression, because this is the same for both. So let's cut this here. And then we also cut the fit method. So this is almost the same, so we don't need this here, and put it up here. The only thing now that we have that is different is the y predicted, because one time we need simply the linear model, and one time we need the linear model and the sigmoid function. So let's create a helper function and call it underscore approximation, which will get our data x, our samples, and then it also gets the weights and the bias. And in our base class we will raise a not implemented error. So this has to be implemented in the derived classes. So now in the linear regression class, let's also create this, and here we will implement this. And in our linear regression model, this is simply the linear model, so we can return this, return the dot product of x and w plus the bias. And then we also have to, or we can cut the fit method from our logistic regression method and implement the approximation method. So here, let's copy this. Or let's remember that we need to have the linear model and then apply the sigmoid function. So let's cut this and let's create our underscore approximation method with self, x, w, and the bias. And then we create our linear model, which is NumPy dot x w plus bias. And then we apply the sigmoid function and return it. So let's return self dot underscore sigmoid of our linear model. So this is the approximation, and now the predict method is a little bit different. So let's in our base class, let's define this predict method, and here we will implement a helper function, and we call it underscore predict, which will get self, x, and also w and b. And also in the base class here we will simply raise a not implemented error. So this now has to be implemented in the derived classes. So we call and return this in our predict method in the base class. So let's return self dot underscore predict and with the test samples, and then now with our calculated weights and the calculated bias. And now in our linear regression class we define this underscore predict, which will get x, w, and bias. So, and here it will get, so this will be the same code. So the dot product of x and w plus the bias, and we can return this in this line, so we don't need this. And then also in the logistic regression we define this as underscore predict with x, w, and b. And then we have the same code here, so we use w and b, then apply the sigmoid, define if it's 1 or 0 and return it. And now we can copy this here and put it in the same file here. And then we are done. So now we have two models, the linear regression and the logistic regression, just in 60 lines of Python, and it looks much cleaner now. So yeah, that's it. I hope you enjoyed this tutorial and see you next time. Bye. Hi everybody, welcome to a new machine learning from scratch tutorial. Today we are going to implement the naive Bayes classifier using only built-in Python modules and NumPy. So the naive Bayes classifier is based on the Bayes theorem, which says that if we have two events A and B, then the probability of event A, given that B has already happened, is equal to the probability of B, given that A has happened, times the probability of A divided by the probability of B. And if we apply this to our case, then our formula is the probability of y, of our class y, given the feature vector x, is equal to the probability of x given y times p of y divided by p of x. and where x is our feature vector, which consists of several features. And now it's called naive Bayes because now we make the assumption that all features are mutually independent, which means, for example, if you want to predict the probability that a person is going out for a run, given the feature that the sun is shining and also given the feature that the person is healthy, then both of these features might be independent, but both contribute to this probability that the person goes out. So in real life, a lot of features are not mutually independent, but this assumption works fine for a lot of problems. And with this assumption, we can split this probability into and use the chain rule. So we calculate the probability for each feature given y and multiply each, and then we multiply it with p of y and divide it by p of x. And by the way, this p of y given x is called the posterior probability. P of x given y is called the class conditional probability, and p of y is called the prior probability of y, and p of x is called the prior probability of x. And now we want to make a classification. So given this posterior probability, we want to select the class with the highest probability. So we choose y, which is the argmax of y of this posterior probability. And now we can apply our formula. And since we are only interested in y, we don't need this p of x, so we can cross this out. And then our formula is this, so y is the argmax of, and then we multiply each class conditional probability and then the prior probability. And then we use a little trick. Since all these values are probabilities between 0 and 1, so if we multiply a lot of these values, then we get very small numbers and we might run into overflow problems. So in order to prevent this, we apply the log function. So we apply the log for each of these probabilities, and with the log or the rules for logarithms, we can change the multiplication sign into a plus sign. So now we have an addition here. And now we have this formula that we need. And now we need to come up with this prior probability. So the prior probability is just the frequency. We can see this in a second. And then what is this class conditional probability? P of x given y. And here we model this with a Gaussian distribution. So here we can see the formula. So this is 1 over and then the square root of 2 pi times the variance of y times the exponential function of minus x minus the mean value squared divided by 2 times the variance. And here we see a plot of the Gaussian function for different means and variances. So this is a probability that is always between 0 and 1. And yeah, with this formulas, this is all we need to get started. So now we can start and implement it. And first of all, of course, we import NumPy as NP. And then we create a class called naive Bayes. And it doesn't need an init method, so we can implement the fit method first. So we want to fit training data and the training labels. And then we also want to implement a predict method. So here we predict the test labels. or test samples. And now let's start. So let's start with the fit method. So what we can do here is, so we need the priors and we can calculate them in this fit method, and we need the class conditional. So here we need the mean for each class and the variance for each class, so we can also calculate these. So let's do this. So let's get the number of samples and the number of features first. And by the way, our input here, the x, is a NumPy ND array, where the first dimension is the number of samples and the second dimension, or the number of rows, is the number of samples, and the number of columns is the number of features. So we can unpack this and say this is x.shape, and our y is a 1D row vector, also of size the number of samples. So this is our input. And now let's get the unique classes. So let's say self classes equals NumPy unique of y. So this will find the unique elements of an array. So if we have two classes, 0 and 1, then this will be an array just with one 0 and one y in it, and one 1 in it. Then let's say the number of classes equals the length of this self classes. And now let's init mean, variance, and priors. So let's say self.mean equals, and we want to init them with zeros at first, and it gets the size. It has number of classes and number of features as tuple here. So it also, for each class, it has the same number of for each class we need means for each feature, and we want to get this, or give this, a data type of float numpy.float64. And we want to do this with the same for the variances. So let's say self.var equals this. And then we want to do self.priors equals np.zeros. And here for each class we want one prior. So this is just a 1D vector of size number of classes with a data type of np.float64. And now let's calculate them. So for each class in self.classes, we only want the samples that has this class as label. So let's call this xc equals x, and then where c equals y. And now we can calculate the mean for each class and fill our self.mean. So we want to fill this row and all columns here, and we say this is xc dot, and NumPy has a ND array has the built-in mean function, so we can say mean along the axis 0. So please check the mean function for yourself. And we want to do the same thing for var. So self var in this row for each column is xc.var. So NumPy also has a var method. and then we calculate the priors, so self priors of this class is equal to, and now what information do we already have if we have the training samples and training labels? So we can say the prior probability that this class will occur is equal to the frequency of this class in the training samples. So we say we get xc dot shape 0. So only this will get the number of samples with this label, and then we divide it by the number of total samples. So, and we have to convert this to a float because we don't want integers here. So let's say float number of samples. So this is the frequency, how often this class C is occurring. And now this is all for our fit method. And now let's implement the predict method. So, and for this we create a little helper method. So let's call this underscore predict self, and this will only get one sample. So here we have we can have multiple samples. So here we say y predict equals, and then we use list comprehension and call this underscore predict method for only one sample, and then we do this for each sample in our test samples, and then we return them. And now we have to implement our underscore predict method. So here what we need now is we need to apply this function. So we have to calculate the posterior probability and calculate the class conditional and the prior for each one, and then choose the class with the highest probability. So let's create an empty list called posteriors equals an empty list. And now let's go over each class. So let's say for index and C in enumerate self dot classes. So here we get also the index and the class label with this enumerate function. And now we can say first we get the prior. So the prior equals, and we already have calculated the priors. So this is the prior of self dot priors with this current index. And now, as I said, then at the end we apply the log function. So let's apply this right here. So let's say np.log, and then create the posterior. So the posterior equals, or let's call this class conditional equals, and then we apply the Gaussian function. So for this, let's create this helper function and call this probability density function with self, and then it gets the class index, and then it gets x. And here we apply this formula here. So we need the mean and the variance, and then apply this function. So first of all, let's get the mean equals, and we already have the mean, so we can say self mean of this class index, and also the variance equals self var of this class index. And then let's create the numerator, which is equals to numpy dot exp, so the exponential function of minus, and then we have x minus mean to the power of 2 divided by, and then 2 times the variance, and then we have the denominator, so denominator equals, and here we have np dot sqrt, so the square root of 2 times, and we have pi. We can also get this from numpy, np.pi times the var, and then we return numerator divided by denominator. So this is our probability density function, and then we can say our class conditional is self dot probability density function of our index and x, and then we want to have the logarithmus, so we say np.log, and then we sum all of them up, so we can use numpy.sum of this, and then we say our posterior equals prior plus the class conditionals, or class conditional, and then we append them to our posteriors, so posteriors dot append posterior, and now we use, or we apply the argmax of this and choose the class with the highest probability. So NumPy also has a argmax function, so this is very easy. So we can now say return self dot classes of, and the index is now the index of the posteriors with the highest probability. So we can say np.argmax of this posteriors, and now we are done. So this is the whole implementation, and now we can run it. So I already have a little test script where I use the scikit-learn library to load a data set and create a data set with 1000 samples and 10 features for each sample, and we have 2 classes. Then we split our data into training and testing samples and the labels. Then we create our naive Bayes classifier, which I import from this file that I have here. And then I fit the training data and the training labels, and then I get the predictions for the test samples, and then I will calculate the accuracy. So let's run this and see if this is working. So yeah, it's working, and we have a classification accuracy of 0.96. So pretty good. So yeah, that's it. I hope you enjoyed this tutorial, and see you next time. Bye. Hi everybody, welcome to a new machine learning from scratch tutorial. Today we are going to implement a perceptron using only built-in Python modules and NumPy. The perceptron can be seen as one single unit of an artificial neural network. So the perceptron is a simplified model of a biological neuron, and it simulates the behavior of only one cell. So let's have a look at this image. Here we have one cell, and our cell gets an input, so it gets input signals, and they are weighted and summed up. And if the whole input signal then reaches a certain threshold, our cell fires a signal and delivers an output. So in our case, it either fires a 1 or a 0. And now if we model this mathematically, then it looks like this. So we have our input features, and they are multiplied with some weights and then summed up. And then we apply an activation function and get our output class. So this is the model, and now the linear part, the linear model, simply looks like this. So this is just a linear function, w transpose times x plus b. So here we multiply and sum up our weights and the bias. So the bias is the w0 here in this picture. And after this linear model, we apply the activation function. And in the simplest case, we simply use the so-called unit step function. And this is defined as it's either 1 if our input reaches a certain threshold, or 0 otherwise. So in this picture, the threshold is 0. So if the input is larger than 0, then the output is 1. And otherwise it's 0. And now this is all we need to model the output. And now the whole output looks like this. So first we apply the linear function, and then we apply the activation function. And now we have to come up with the weights and the bias. And for this we use a simple update rule that is called the Perceptron rule. So we look at each training sample xi, and for each training sample we then apply the update step, and this is defined as the new weight is the old weight plus the delta weight, and the delta weight or delta w is defined as alpha times the actual label minus the predicted label times the training sample x. And here alpha is a learning rate between 0 and 1. So this is just a scaling factor. And now let's have a look at what this update rule means. So let's have a look at the 4 possible cases in a 2-class problem. So our output can be 1, the actual label can be 1, and the predicted label is also 1, then the difference is 0, so we have no change for our weights here. And the same is if the actual class is 0 and the predicted class is also 0, so correctly classified, then the difference is 0, and again no change for our weights. But now what happens if we have a misclassification? So if the actual class is 1 and the predicted class is 0, this means that our weights are too low, and then we see that the difference is 1, so our weights are increased here. And if the actual class is 0 and the predicted class is 1, then our weights are too high, and we see that the difference is -1, so then our weights are decreased. So the weights are pushed towards the positive or negative class in case of a misclassification. And this is a simple and intuitive rule, but it works. And this is all we need. So we look at each training sample and then apply the update rule, and then we do this a couple of times. So we iterate for a certain number of iterations, and then we have the final weights and are done. So this is all we need to know, and now we can get started and implement it. So first of all, of course, we use NumPy. So we import NumPy as NP. And then we create a class and call it Perceptron. And it gets an init method, of course. And here it has self, and it gets the learning rate, and I will give this a default of 0.01. Then it gets a number of iterations, so n iters, and I will also give this a default, let's say 1000. Then I will simply store them, so I will say self.lr equals learning rate and self.n iters equals n iters. Then we create a deactivation function. So let's say self.activation func equals, and now let's create this here. And as I said, the activation function is simply the unit step function. So let's call this unit step func with self and an input x, and we could simply say return 1 if x is larger or equal than 0, and else return 0. But we see later that this would only work for one single sample, but we see later that we want to apply the activation function in the predict method for all the test samples. So we want to apply this for a ND array as well. And for this we can use a simple function that is called numpy.where. So we return numpy.where, and this will get a condition, so x is larger or equal than 0. And if the condition is true, then we return 1, and otherwise 0. So this will work for one single sample, but also for multiple samples in one vector. So now this is our activation function. So now we can say self.activation func equals self.unit step func. And now let's also create the weights. Say self.weights equals none, and self.bias equals none. So now that we know that we have to implement them or get them, and now we implement two functions. As always, we implement the fit and the predict method. So first define the fit method with x and y. So this gets the training samples and the training labels. And then of course, oh, I forgot the self. And then we also define the predict method, which gets self and then the test samples. And now we start with this predict method, because this is very simple. Let's have a look at the approximation of our output again. So here first we apply this linear function and then the activation function. So let's do this. So first the linear function. So let's say linear output equals, and this is W transpose times X plus the bias. And W transpose times X is nothing else but the dot product. So we can use NumPy dot of X and self dot weights plus self dot bias. So now we have the linear function, and now we apply the activation function. So we say y predicted equals self dot activation function, and as an input it gets the linear output here, and then we simply return the y predicted. So this is the whole predict method, and now let's jump to the fit method. So first of all, let's get the dimensions of the x vector. So this is an ND array of size m times n, where m, or the number of rows, is the number of samples, and n, or the number of columns, is the number of features. So we say n samples and n features equals x dot shape. And now we init our weights, so we have to give them an initial value, and we can simply set them to 0 in the beginning. So we say self.weights equals numpy.zeros of size, number of features. So for each feature we put a 0 here for our weight, and also our self.bias, this is simply 0. And now we can start, or one more thing we have to do is we want to make sure that our y only consists of classes 0 and 1. So let's say y underscore equals, and now let's convert all the values to 0 or 1 if this is not already the case. So we use list comprehension for this. So we say 1 if I is larger than 0, else it's 0 for I in y. And now let's convert this to a NumPy array. So now we have our y, and now we can start the training. So let's again have a look at this update rule. So we want to look at each training sample, and we also want to do this a couple of iterations. So we need 2 for loops here. So let's say the first one, for underscore, because we don't need this, in range self.n iters. So this is the number of iterations we defined. And then our second loop, and for this I used the enumerate method, so I can say for index and also x, y in enumerate x. So I want to iterate over the training samples, and the enumerate function will give me the index and then also the current sample. So these are our 2 loops, and now sorry, let's apply this update rule. So we have to calculate the predicted value and then apply the update. So let's say the linear output equals numpy dot of the current sample and our self.weights plus the self.bias. Then we apply the activation function and get the predicted value. So y predicted equals self.activation function of the linear output. So here we can see that in this case we use it for only one sample, and here down in the predict method we use the activation function for multiple samples, and that's why we need this numpy where function here in our activation function. So yeah, and now let's continue. So now we have our predicted y, and now let's have a look at the formula again. So we have the learning rate times the difference and then times x. So let's call this update equals self.learning rate times, and here we have the actual label, so y underscore of this current index minus y predicted, and then we say self.weights plus equals update times xi and self.bias plus equals update times 1. So we don't need this times 1. And now we are done. So this is the whole implementation of the Perceptron. And now let's test this. So here I've already written a little test script here. So I import the Perceptron here, and then I will create two blobs. So I can use this from the sklearn module. I can use a function that is called make blobs. So this will create two classes, and then I will split our data into training samples and test samples, and training labels and test labels. Then I will create a perceptron. I will fit the training data, and then I will predict the test labels, and then I will calculate the accuracy, and I will also plot this. So let's run this, and I hope I didn't forget anything. So now here is the plot. So here we see our two blobs, and here we have our linear decision boundary. So this is the decision function that our perceptron generated, and we see that it separates our two classes perfect here. So, and we also see that our accuracy is 1, so it's perfect in this case. And yeah, we see that the perceptron works. And one thing that we should be aware of is that the perceptron only works for linearly separable classes. So if classes can be separated with a linear function, like here in our case, let's have a look at this again, then it works very well, but otherwise not so much. And for further improvements, we can try out different activation functions, for example the sigmoid function, and then apply a gradient descent method rather than the perceptron rule in order to update our weights. But yeah, for now that should be all I wanted to show you, and I hope you enjoyed this tutorial, and see you next time. Bye. Hi everybody, welcome to a new machine learning from scratch tutorial. Today we're going to implement the SVM algorithm using only built-in Python modules and NumPy. The SVM, or support vector machine, is a very popular algorithm. It follows the idea to use a linear model and to find a linear decision boundary, also called a hyperplane, that best separates our data. And here the choice as the best hyperplane is the one that represents the largest separation or the largest margin between the two classes. So we choose the hyperplane so that the distance from it to the nearest data point on each side is maximized. So if we have a look at this image, then we want to find a hyperplane, and the hyperplane has to satisfy this equation, w times x minus b equals 0. And we want to find the hyperplane so that the distance to both classes is maximized. So we use the class +1 here and -1 here. So this distance, or the margin, should be maximized. And first let's have a look at the math behind it. So it's a little bit more complex than in my previous tutorials, but I promise that once you have understood it, the final implementation is fairly simple. So we used the linear model w times x minus b, that should be 0, and then our function should also satisfy the condition that w times x minus b should be greater or equal than 1 for our class +1. So all the samples here must lie on the left side of this equation, or this line here, and all the samples of the class -1 must lie on the right side from this equation. So if we put this mathematically, then it must satisfy w times x minus b should be greater or equal than 1 for class 1, or it should be less or equal than -1 for class -1. So if you put this in only one equation, then we multiply our linear function with the class label, and this should be greater or equal than 1. So this is the condition that we want to satisfy. And now we want to come up with the w and the b, so our weights and the bias. And for this we use the cost function and then apply gradient descent. So if you're not familiar with gradient descent already, then please watch one of my previous tutorials, for example the one with linear regression. There I explain this a little bit more in detail. So now let's continue. So we use a cost function here, and in this case we use the hinge loss, and this is defined as the maximum of 0 and 1 minus, and here we have our condition yi times our linear model. So what this means is if we plot the hinge loss, then here the blue line is the hinge loss. So this is either 0 if y times f is greater or equal than 1. So if they have the same sign, then it's 0. And so if they are correctly classified and are larger than 1, then our loss is 0. So this means, if we have a look at this image again, if for the green class, if it lies on this side, then it's 0. And for the blue class, if it lies on this side, then it's also 0. And otherwise, then we have a linear function. So the further we are away from our decision boundary line, the higher is our loss. And so this is one part of our cost function, and the other part is, as I already said, we want to maximize the margin here, so between these two classes, and the margin is defined as 2 over the magnitude of w. So this is dependent on our weight vector. So we want to maximize this, and therefore we want to minimize the magnitude. So we put this or add this to our cost function. So we also put this term, the magnitude of w to the power of 2 times a lambda parameter. And then here we have our hinge loss. So the lambda parameter tries to find a trade-off between these two terms. So it basically says which is more important. So we want to, of course, we want to have the right classification. We want to lie on the correct side of our lines, but we also want to have the line such that the margin is maximized. So if you look at the two cases, if we are on the correct side of the line, so if yi times f of x is greater or equal than 1, then we only have this term, because this is the hinge loss is 0, and otherwise then our cost function is this here. And now we want to minimize that, so we want to get the derivatives or the gradients of our cost function. So in the first case, if we are greater or equal than 1, our derivative is 2 times lambda times w. So, and here we only look at one component of our w, so we get rid of the magnitude, and the derivative with respect to the b is 0. So please double check that for yourself here. I will not explain the derivatives in details. And in the other case, so if yi times f on x is not greater or equal than 1, then our derivative with respect to the w is this equation here, and the derivative with respect to our bias is only yi. So again, please double check that for yourself. And then when we have our gradients, we can use the update rule. So the new weight is the old weight minus, because we use gradient descent, so we go into negative direction, minus the learning rate or the step size times the derivative. So these are our update rules, and now I hope you've understood the concept and the math behind this, and now we can start implementing it. So this is now straightforward. So first of all, we import NumPy, S and P, of course, and then we create our class svm, which will get an init method, and here I will put in a learning rate, which will get a default value of 0.001, and it will get a lambda parameter, which will also get a default, and I will say this is 0.01. So this is usually also a small value. And then it will get the number of iterations for our optimization, which will get the default of 1000. So then I will simply store them. So I will say self.lr equals learning rate, self.lambda param equals lambda param. So note that I cannot use lambda here, because lambda is a keyword in Python for the lambda function. So yeah, then self.n iters equals n iters. Then I will say self.w equals none and self.b equals none. So I have to come up with them later. And then we define our two functions. So as always, one is the predict function, where we fit the training samples and the training labels. And the this is the fit method. And the other one is the predict method, where we predict the labels of the test samples. And now let's start with the predict method, because this is very short. So we want to, as I said, if we look at the math, we apply this linear model, and then we look at the sign of this. So if it's positive, then we say it's class 1, and if it's negative, then we say it's class -1. So we say linear output equals NumPy dot, so the dot product of x and self.w minus self.b, and then we choose the sign, so we can simply say return NumPy dot sign of this linear output. So this is the whole predict implementation. And now let's continue with the fit method. So first of all, as I said, we use the classes +1 and -1 here. So we want to make sure that our y has only -1 and +1. So oftentimes it has 0 and 1. So let's convert this. So let's say y underscore equals, and here we can use NumPy dot where. This will get a condition, so we say y. If this is less or equal than 0, then we put in -1, and otherwise we put in +1. So this will convert all the zeros or smaller numbers to -1 and the other numbers to +1. And now let's get the number of samples and the number of features, and this is simply x dot shape, because our input vector x is a NumPy ND array, where the number of rows is the number of samples and the number of columns is the number of features. Then we want to initialize our w and our b, and we simply put in zeros in the beginning. So we say self.w equals NumPy zeros of size n features. So for each feature component we put in a 0 for our weight component, and then we say self.b equals 0. And now we can start with our gradient descent. So we say for underscore, because we don't need this, in range self dot and iter, so the number of iterations we want to do this. And then we iterate over our training samples. So I say for index and xi in enumerate x. So this will give me the current index and also the current sample. And now what I want to do now is, let's have a look at the math again. So I want to calculate the weights or the derivative of our cost function with respect to the w and with respect to the bias. And here first I look if this condition is satisfied. So I will say, and the condition is yi times our linear function. So I say condition equals y underscore of the current index times, and then the linear function, so NumPy dot of the current sample and our self.w minus self.b. This should be greater or equal than 1. So if this is satisfied, then the condition is true, and otherwise it's false. So now I say if condition, so if this is true, then our derivatives look like this. So the derivative with respect to the b is just 0, and so we only need this. So I say so it's 2 times lambda times w, and then in our update we go in, so we say the new weight is the old weight minus the learning rate times this. So I write this in one step. So I say self.w minus equals self.learning rate times, and now here we have 2 times self.lambda parameter times self.w. So this is the first update, or if our condition is satisfied, and we only need this update, and otherwise we say self.w minus equals self times lr, the learning rate, times, and let's again have a look at the equation. So it's 2 times lambda times w minus yi times xi. So 2 times our lambda times the w minus NumPy dot, so I want to multiply our vectors xi and yi, so the y underscore of the current index. So this is our update for the w, and our self dot b is minus equals self times learning rate times the derivative, and the derivative is only or just yi, so only y underscore of the index. And now we're done. So this is the whole implementation, and now let's test this. So I've written a little test script that will import this SVM class, and then it will generate some test samples. So it will generate 2 classes, and then I will create my SVM classifier and fit the data, and then I wrote a little function to visualize this. So you can find the code on GitHub, by the way, so please check that out for yourself. And now if we run this, so let's say Python svm underscore test.py, and now this should calculate the weights and the bias, and it should also plot the decision function, so the yellow line and the 2 lines on both sides here, and we see that it's working. So yeah, that's all about the SVM. I hope you enjoyed this, and if you liked this, please subscribe to my channel, and see you next time. Bye. Hi everybody, welcome to a new machine learning from scratch tutorial. Today we are going to implement a decision tree using only built-in Python modules and NumPy. A decision tree is a very simple but powerful concept. The idea is to build a tree that splits our data such that we have the best separation of our classes. A decision tree is also the basis for the very popular random forest model, which we will implement in the next tutorial, so I hope you will stick with me. And as always, we will start with the theory first. So let's look at an example to understand the concept and the math behind the decision tree. Let's say we want to predict if a person is walking or taking the bus to go to work. And we have 10 observations or 10 samples with 2 different features. So we have the feature if it is raining, and then we have the feature how much time do they have. And then we have the prediction or the class label, yes or no. And now we want to build our tree that splits our data. So we put all the samples in the root node, and then we apply a question. So we ask if it is raining, and if the answer is yes, then we go to the right and we put all the samples where the answer is yes, so these 3, into the right node, and if the answer is no, then we go to the left and put all the other samples in the left node. And here on the right we can immediately say that the answer is no, they don't walk, so we put return the class label 0. And here on the left we can further split the data and grow our tree. So we ask the next question, so do they have more than 10 minutes? And again, if the answer is yes, then we go to the right and put all of the samples where they have more than 10 minutes in the right node, and all the other ones in the left node. And then again, here we can say that the answer is yes, or the class label is 1, and here the class label is 0. And we could also stop with the growing here and return the most common class label. So here we can say that it's more likely that they will walk. but we could also further split our data, but we don't want to grow our data too much because we don't want to overfit our data, but we also want to have a good prediction. So this is the concept of how the decision tree works. And now the only thing that we have to find out is at which node we want to apply which question. So why do we ask for rain at first and not for the time? And why do we ask for the time is greater than 10? And why don't we ask for if it's greater than 5 or greater than 20? So this is the so-called best split feature and best split value or split threshold that we want to find out. So the concept is at each node, we want to find the best split value and the best split threshold and store them. And this is our training phase. And later, when we want to predict a new test sample, then we start at the top and then we traverse our tree and apply the questions or the features that we stored and go to the left or to the right until we reach a leaf node. So a leaf node is the node at the bottom. And then we apply the most common label that we stored based on our test samples. So this is the concept. And now how do we find out the best split? So for this we need some math. So we calculate the entropy, and the entropy is a measure for uncertainty. So the formula is minus, and then we have the sum of p of x times log of p of x. And p of x is the number of occurrences over the total number of samples. So in our example, we have 10 samples, and 5 times the answer is, or the label is 0, and 5 times the answer is 1. And then we have, our entropy is minus 5 over 10 times log of 5 over 10 minus, and then we look at the next label, so 1. Again, we have 5 labels, so minus 5 over 10 times log of 5 over 10. And if you calculate this, then this is 1. So this is the worst possible case. So here in the first node, we cannot make a prediction if it is 1 or 0, because we have an equal amount of both samples or both classes here. So 1 is the worst possible case. And like here, the entropy here would be 0. So this is the best case. Here we are very certain that we have the class 0. And now, so we calculate the entropy, and then we split our data and calculate the entropy for our childs. And then we calculate how much information we gain through this split. And this measure is actually really called information gain. And this is calculated by the entropy of the parent minus a weighted average of all the child entropies. So like in our example, we have the root node with our 10 observations. And then on the left side, we have 7 observations with here 2 zeros and 5 ones. And on the right side, we have 3 zeros. So our entropy is the entropy of the parent minus 7 over 10 times the entropy on the left side plus 3 over 10 times the entropy of the right side. So this is the information gain. And now we do a greedy search. So we go over all the possible features and over all the possible feature values or thresholds. So for rain, we check if it's yes or no. or it means 1 or 0. And if the answer, and for the time feature, we check for 5, 10, 15, 20, 25, and 30. So we do a greedy search, and then we store or select and store the best feature and the best threshold. So this is the concept. So let's look at the approach a little bit more in detail. So first we have the training phase where we want to build our tree. So we start at the top node, and at each node we select the best split based on the best information gain. And we do a greedy search, so we loop over all features and over all thresholds. Then we save the best split feature and split threshold at each node, and we build the tree recursively. And we also have to apply some stopping criteria to stop growing. And in our example, we will use a maximum depth. So for example, we say if the depth reaches 5, then we would stop. And we use a minimum samples at a node. So for example, we could say if we have less than 5 samples in a node, then we don't split any further. And if we have no more class distribution in a node, like here, then we can no longer split because we only have class 0 labels here. So these are our stopping criteria that we need. And then when we have a leaf node, then we store the most common class label of this node. So here we store 0, 1, and 0. So this is our training phase. And then later, when we do the testing with new samples, then we traverse the tree, and we also do this recursively. So we implement a function that calls itself. And at each node, we look at the best split feature of the test feature vector and go left or right depending on if the value of this feature is smaller or equal than our threshold that we stored. And then when we reach the leaf node or the bottom, we return the stored most common class label. So this is the concept of the decision tree. And now I think I will stop this video here, and we will continue in the next part, or in the second part, with the implementation. So see you then. Hi everybody, welcome to the second part of the decision tree tutorial. If you haven't watched the first part, then please do so, because there I will explain the theory. So here we continue with the implementation, and we can start right away. So we say import NumPy as NP, and then before we implement the decision tree class, we will first create our entropy method to calculate the entropy, and we implement this as global function. So we say define entropy, and this will get a vector y of all our class labels. And let's have a look at the formula. So we have to calculate the number of occurrences, and we can do this with a function, and we call this hist or histogram, and we can use NumPy bin count of y. So this will calculate the number of occurrences of all class labels, and then we divide them by the number of total samples. So we say piece equals hist divided by length of y. And then we apply the actual formula. So we say minus the sum of p of x times the log of p of x. So we can do this in one line and say return minus NumPy sum. And here we use list comprehension. So we can say p times NumPy log 2 of p for all p's in PS. And we also have to use a condition if p is greater than 0 because the log is not defined for negative numbers. So this is the entropy. And now we also implement a helper class and call this node. So here we will store the information for our node. So this will get an init, which gets self. And then let's have a look at this. So if we are in the middle, then we want to store the best split feature and the best split threshold. And we also want to store the left and the right child trees because we need them later. And if we are at a leaf node, then we also want to store the actual value here, so the most common class label. So we say feature equals none, threshold equals none, left equals none, right equals none. And then we use a little trick here. So we use an asterisk and a comma, and then we say value equals none. So now if we want to use this value parameter, we have to use it as a keyword only parameter. So later when we create our leaf node, which only gets the value, then we also have to write value equals something. So then it's clearer that this is a leaf node. And here we simply store them. So we say self feature equals feature, self threshold equals threshold, self left equals left, self right equals right, and self value equals value. And now we also create a little helper function to determine if we are at a leaf node. So define is leaf node, which gets self. And here we simply say if we have a value, then we are at a leaf node, and otherwise not. So we return self.value is not none. So if we have a value, then we return true. And this is our helper class for the nodes. And now we can start with the actual decision tree class. So this also gets an init, which gets self, and then it will get some stopping criteria. So we call this min samples split, and by default, let's say this is 2. So the minimum samples required to further split our tree, then the max depth, and by default this is 100. And then also it gets a parameter that we call the number of features, or n feats. And this is none, so we don't need this, but we can specify it. So as I said, we do a greedy search over all the features, but we can also only loop over a subset of number of features. And then we randomly select this subset. So this is one of the random factors. And that's also one of the reasons why it's called random forest, if we extend our decision trees to a random forest. So this is one random factor. And now we simply store them. So we say self.minSampleSplit equals minSampleSplit, self.maxDepth equals max depth, self.n features equals n features. And we also create a root, and in the beginning this is none. So we later need to know our root so that we know where we should start traversing our tree. And now we implement the fit method, which gets the training data and training labels. So here we want to grow our tree, and then it gets the predict method with the test labels. So here we want to traverse our tree. So let's start with growing our tree. So we say self.root equals, and now we call and create a helper function self.growTree, which gets x and y. And we also apply a safety check. So we say self.nFeeds equals x.shape of 1. So this is a NumPy and D array, and the second dimension is the number of features. If not self.nFeeds, so if this is not specified, if this is none, then we simply take the maximum number of features, and otherwise we take the minimum of self.nFeeds and x.shape 1. So this just makes sure that it can never be greater than the actual number of features. And now we implement the grow tree method, which gets self, and then it gets x and y, and also a depth, and this is 0 in the beginning. So we need to keep track of the depth. And now let's do this. So first let's get the number of samples and the number of features. This is x.shape. And then we also want to get the number of different labels. So this is the length of NumPy unique of y. So all the different labels. And now first, what we do here is first we apply our stopping criteria. So we say if, and now let's again have a look what we said. So we want to check for the maximum depth, then the minimum samples required, and if we have no more class distribution. So we say if, and we say depth is greater or equal than self max depth, or if the number of different labels equals 1. So if we have only one class at this node, or if we have number of samples is smaller than the minimum samples required. So if this is true, then we are at a leaf node. So we say leaf value equals self dot most common label of this y. And now we create and return our leaf node. So we say return node, and then we have to say value equals leaf value. And now it gets clear why I used this asterisk. So here I have to use the value as keyword. And now it's clear that this is a leaf node. And now we also need this helper function to get the most common label. So let's write this down here. So define most common label, which gets self, and then it gets a vector of the class labels. And for this we use a Python module, the counter module. So we say from collections import counter. So I talked about this in previous videos already. Please check that out if you're not familiar with the counter module. So here we can create a counter object, counter equals counter of y. So this will calculate all the number of occurrences for all the y's, similar to the NumPy bin count. And then we have a most common function. So we say most common equals counter dot most common of 1. So we only need the very most common label. And this will return a list of tuples. So we want to have the first element of the list. So this is the very most common tuple. And in the tuple there is the value stored and also the number of occurrences. So we only need the value. So we again say index 0. So please double check that for yourself. And then we return this. This will determine the most common label. So now we have that here. And now if we didn't meet the stopping criteria, then we continue. So first we select the feature indices. So feature indices equals NumPy random choice. And this will get the number of features. So it will select random numbers from between 0 and the number of features. And the array should be of size self.n feats that we specified. And we also say replace equals false because we don't want to have the same indices multiple times. And now we do our greedy search. So we say best thresh and best, let's do it the other way around. Best feature and best thresh equals self dot best criteria. And this will get X and Y and all the feature indices. So this is another helper method. So let's define it here. Define itself best criteria, which gets self and X and Y and the feature indices. So here we do our greedy search. So we say best gain equals -1. So we want to go over all the features and all the feature values and calculate the information gain. So now let's say split index and split threshold equals none. So both of them are none. And then we have our first loop. So for feature index in feature indices. And now we only want to select the column vector of this X. So we say X column equals X of, and we want to have all samples, but only at this index. And then we want to go over all the possible thresholds. So we say thresholds equals NumPy unique of X column. So we don't want to check the same value twice. So like in this example here, we would check for 30, 15, 5, 10, 20, and 25. And now we go over all the possible thresholds. So we say for threshold in thresholds. And now we calculate the information gain. So we say gain equals self.information gain, which gets Y and the column vector and also the current thresholds. And then we say if gain is greater than our best gain, then our new best gain is the current gain, and our best split index is the current feature index, and our best split threshold is the current threshold. And at the end, we want to return them. So we return the split index first, and then the split threshold. So this is the greedy search, and now we need another helper function to calculate the information gain. So let's say define information gain with self, and then it gets y and an x column and the threshold. So let's call this split thresh. And now let's say let's have a look at the formula again. So so we want to calculate the entropy of the parent and then a weighted average of the children. So we calculate the parent entropy, then we generate a split, then we calculate the weighted average of the child entropies, and then we return the information gain. So the parent entropy, we can simply say parent entropy equals entropy, because we already have this function. So parent entropy of y. Then we generate our split. So we say left indices and right indices equals self.split, and we split based on this x column and a split threshold. So we need another helper function. So I hope you can still follow me. I hope I try to explain everything as clear as possible, but the code is a little bit more complex than usual. But yeah, let's continue. So let's say define split self, and then it gets x column and our split threshold. And here we can say left indices. So here we apply our question, and we can use a function that is called NumPy arc where. And here we asked if the value of x column is smaller or equal than our split threshold. So this will return an array where all these conditions are true for all the values in our x column. And we want to flatten this array because we only want a 1D vector. So please check that for yourself. And we do the same for the right indices. So we say NumPy arc where, and here we check if x column is greater than our split threshold, and then we flatten this, and then we return the left indices and the right indices. So now we have the split function, and now if we have the with this function we generate the split here, and first we check if length of the left indices is 0 or the length of the right indices is 0. Then we can immediately return 0 as information gain, and otherwise we continue. So we calculate the weighted average. So we need the number of total occurrences of the number of our samples. So this is length of y, and then the number of our left samples and the number of our right samples equals leng left indices and leng right indices. Then we calculate the entropy. So we say EL and ER equals entropy of Y of all the left indices and entropy of Y of all the right indices. And now our child entropy equals the weighted average. So we say NL divided by N times the left entropy plus, and now NR divided by N times the right entropy. So this is the child entropy, and now let's calculate the information gain. This is just the parent entropy minus the child entropy, and now we return it. So return the information gain. So now we have this. So now this function is complete, and now we can have to continue with the growing. So now after we have selected the best criteria, we want to split our tree with this best feature and best threshold. So we say left indices and right indices equals self.split. So again, here we can use our split function. So we say x of, and now we have to be careful. So now we want to have all samples, but only the best feature index. So this is a column, and here we put in the best threshold. And now with our left and right indices, we can continue growing. So we go to the left and say left equals, and we call this function here in itself recursively. So we say self.growTree, and here we say x, and then we only want the left indices, but we want all the features. So, and as y, we only want the left indices. And then we also say depth plus 1. So now our depth is increased by 1. And now we do the same thing for the right side. So we say right equals growTree with the right indices. And now we return a new node in the middle. So this will get the best feature, the best threshold, and the left and the right childs, but no value here. So this is the growing method, and now the only thing left is to implement the predict method, and I promise this will be fairly easy. So we only need one helper function, so we say return NumPy array, and here again we use list comprehension. So we traverse our tree, so self.traverse tree, where we put in one sample for all the samples in capital X. So this is our predict method, and now let's implement the traverse tree method as last thing. So this will get self and one sample, and it also gets a node where we start. So here we have to put in self.root in the beginning because we start at the top. And here we also do this recursively. So first we can check for the stopping criteria. So we check if we have reached a leaf node. So we can say if node is leaf node. So that's why we implemented this helper function. Then we return node.value, because if we are at a leaf, we also have a value. And otherwise, we apply our question. So we go to the left or the right. So we say if x of this node, the feature index that we stored, is smaller or equal than the threshold that we stored at this node, then we return self.traverse tree. So we go to the left side and we put in x and node left. So that's why we start the left and the right nodes at the nodes. And otherwise we return self.traverse tree of x and node.right. So yeah, this is the whole traverse implementation. And now we are finally done. This is the whole implementation that we need for a decision tree. And let's check this. So I've written a little helper script, a test script, where I implement this decision tree class, and I use the data set, the breast cancer data set from the scikit-learn module. And I will split our data in training labels and training samples and test labels and test samples. Then I will create our decision tree and fit the data, then predict the test data and calculate the accuracy. So let's check. Let's run this script and check if everything's working. Needs a little time to... Sorry, as traverse tree missing one positional argument node. Self.traverse tree x. Oh, self.root must be here, not here. So let's clear this and give this another try. And fingers crossed, node object has no attribute feature index. So this is, how did we call it? Just feature, sorry. If node dot feature threshold, threshold, So one more time. I hope I have no more typos. So yeah, now we have the accuracy and everything's working. And yeah, I hope you enjoyed this tutorial. If you liked it, please subscribe to the channel. And in the next tutorial, we will continue by extending this decision tree to the random forest model. So yeah, see you then. Bye. Hi everybody, welcome to a new machine learning from scratch tutorial. Today we are going to implement a random forest using only built-in Python modules and NumPy. The random forest algorithm is one of the most powerful and most popular algorithms, so I'm very excited that we can finally implement it in this tutorial. In the last tutorial I explained how a single decision tree works, so if you haven't watched the previous tutorial yet, then please do so. Because our random forest model and also the implementation is based on the decision tree model from the last time. So if you have understood the decision trees, then the approach of the random forest is very easy to understand. If we have a look at this image here, then this shows the whole idea. So the idea is to combine multiple trees into a forest. So we train multiple trees and each tree gets a random subset of the training data. Thus the word random. We then make a prediction with each of the trees at the end, and we make a majority vote then to get the final prediction. So this is the whole idea. And a random forest has some advantages compared to only one tree. For example, by building more trees, we have more chances to get the correct prediction. And we also reduce the chance of overfitting with a single tree. So typically the accuracy of a random forest is higher than with a single tree. And that's why it's so powerful. So yeah, now we can jump right to the implementation. So of course we import NumPy as NP, and then we also import the decision tree class from the last time. So we say from decision tree import decision tree, and now we can start. We create our class decision tree, and now we have the random forest. So now we create our random forest class, and this will get an init. So, and this will get the number of trees we want to have in our forest. So let's say number of trees equals 100 by default. And then it also gets all the parameters from our decision tree initializer. So it gets the minimum samples required for a split, it gets the maximum depth, and it gets an optional number of features for some more randomness. So let's just copy and paste this here. And then we store all of them. So we say self.number of trees equals n trees, self.min sample split equals min sample split, self.max depth equals max depth, and self.n feeds equals n feeds. And then we implement our predict and our fit method. So the predict method has the test data, and we start with the fit method. So we say fit self, and this will have the training data and the training labels. And one more thing that we want to have, and I can put it here first. So we want to have an empty array of trees where we want to store each single tree that we now are going to create. So we say self.trees equals, and this will be an empty list. And then in the fit method, we want to make sure that the list is empty again. And now we start training our trees. So we say for underscore, because we don't need this, in range self.number of trees. And now we create our tree. So we say tree equals decision tree, and this will get all the parameters. So it gets min sample split equals self.min sample split. Then it will have the max depth equals self.max depth, and the number of features equals self.number of features. And now what we want to do is we want to give our tree a random subset. So let's define a global function here. Let's call this is also called bootstrapping. So let's call this bootstrap sample, which will get X and Y. And now we first look at how many different number of samples we have. So n samples equals X dot shape. So as always, this is a NumPy ND array where the first dimension is the number of samples and the second dimension the number of features. And now we make a random choice. So we say indices equals NumPy random choice. And here we put in the number of samples as integer. This means that it will make a random choice between 0 and the number of samples. So our indices lie in this range, and the size will be of size number of samples 2. But we also say replace equals true. So this means that some of the indices can be there multiple times and others get dropped. So we randomly drop some of the samples and use only a subset. And then we return the x of these indices and also the y of these indices. So now we only have these selected samples, and now we can train our tree with this. So first we say x sample and y sample equals bootstrap sample with x and y, and then we say tree.fit x sample and y sample, and then we simply append this to our tree list. So we say self.trees.append tree. And now we are done with the training phase. And now when we predict it, so we make a prediction with each of our trees. So we say tree preds or tree predictions equals, and here I will use a list comprehension and then convert this to a NumPy array. So here I say tree.predict x for tree in self.trees. So for each trees now we make, or we call the tree predict method. And now we want to do the majority vote, but now we have to be careful, because what we get here is, let's say, for example, we have 3 trees and 4 samples. And then let's say our first tree, for simplicity, just does once as predictions. So for each sample, it will have a 1 here. And the second tree just makes zeros, so we have zeros. And then the third tree also just predicts once. So, and then again, this would be an array, this would be an array, and this would be an array in this array then. And now we want to do the majority vote. So now what we actually want is, we want arrays that look like this. So we want to have 101, 101, 101, and 101. So this one, from all of the trees, we want to have the corresponding predictions. So we convert it to this structure, and there's a very nice function from NumPy that is doing exactly this. So we say tree preds equals NumPy swap axis with this tree predictions, and then we swap axis 0 and axis 1. So this is doing exactly this. And now we can do the majority vote. So we say y prediction equals, and now we predict the most common label for each of these tree predictions. So now if we have 101, 101, 101, so now we go over them and make a majority vote, then over them, and then over them. So we use list comprehension again, and we say most common label of a tree prediction for each tree prediction in tree predictions, and then we convert this to a NumPy array and return it. And now the only thing left that we need is the most common label function. And we also needed this in the decision tree class. So here we have the most common label function as a class function. So here, as you see, we'll need this a lot of times, so it might be better to do this as a global function. So we put this here, and you might even put it in another file and call this from a helper class or something, but we just put it here. So I will not explain this again. If you don't know how this works, then please watch the last tutorial. So we don't need self anymore. And we also need to import from collections, import the counter module. And now we can do the majority vote, and now we are done. So I have a little test script here to test our class. So I will import the breast cancer dataset from the sklearn module. Then I will generate some training and test labels. Then I will create our random forest instance. And here I just use 3 trees because training might take some time and we didn't optimize our code. So in our video I just used 3 now. Then I will fit the data and I will predict the test data and then calculate the accuracy. So let's run this and hope that everything is working. And we made a mistake, so we say self. Oh, we want to append it to our trees, of course. And now one more try. Fingers crossed. And now we have the accuracy. So now we see that our model is working. And yeah, I hope you understood everything. And if you liked it, please subscribe to the channel and see you next time. Bye. Hi everybody, welcome to a new machine learning from scratch tutorial. Today we are going to implement the principal component analysis, or PCA, using only Python and NumPy. The PCA is a nice tool to get linearly independent features and also to reduce the dimensionality of our dataset. So the goal is to find a new set of dimensions such that all the dimensions are orthogonal and hence linearly independent and ranked according to the variance of data along them. So this means we want to find a transformation such that the transformed features are linearly independent and the dimensionality can then be reduced by taking only the dimensions with the highest importance. And those newly found dimensions should minimize the projection error, and the projected points should have a maximum spread, or which means the maximum variance. So let's look at an image to understand this better. So let's say our 2D data is distributed like this, and now we want to project it into 1D. And now what we want to do is we want to find the axes that are orthogonal to each other. And when we project our data onto these axes, then our new projected data should have the maximum spread. So on the left side, these are the correct principal axes. So if we project them in 1D, so on the largest principal component, if we project our data on this axis, then they have the maximum spread. And for example, if we look on the right side, so these are incorrect axes. So let's look at how the projected data would look like for. So on the right side, we made it even worse and projected it on the y-axis. So these are clearly wrong because here we can see that a lot of data is on the same spot, so we don't have any more information about them. But here on the left side, the projected data has the maximum spread. So we can contain most of the information about the data, and also the projection error, which means this would be the lines from here to the axis. This is minimal, whereas on the right side, so here we have to make a long, very long projection line for each point. So the left side is the correct answer. And now how do we find these principal components? So for this, as I said, we want to maximize the variance. So we need some math. So we need the variance of a sample X. And this is calculated as 1 over the number of samples. And then we have the sum over each component minus X bar. And X bar is the mean value. So we subtract the mean value from our data set. And now we also need the covariance matrix. So this indicates the level to which two variables vary together. And the covariance matrix of two variables is defined as this. So 1 over n, and then again the sum. And here we subtract the mean. And again here also the mean and then transposed. And in our case, we want to have the covariance matrix with both of our x's. So this is also called the autocovariance matrix. So we have to calculate this, and then our problem is reduced to an eigenvector or eigenvalue problem. So I will not go into detail about eigenvectors here, but I will put some links in the description if you want to read more. But what we have to do is we have to find the eigenvectors and eigenvalues of this covariance matrix. And the eigenvectors point then in the direction of the maximum variance, and the corresponding eigenvalues indicate the importance of its corresponding eigenvector. So now if we have a look at this image again on the left side, so these two vectors that I've drawn here, they correspond to the eigenvectors of the covariance matrix of our data set. So this is what we have to do, and here I've written the approach. So first we subtract the mean value from our X or from our data set, then we calculate the covariance matrix, then we have to calculate the eigenvectors and eigenvalues, then we sort the eigenvectors in decreasing order according to their eigenvalues. And then we can specify how many dimensions we want to keep. And then we choose only the first k eigenvectors. That will then be the new k dimensions. And then we transform the original data into these new dimensions by projecting them. This is simply a dot product of our data with the eigenvectors, and then we are done. So this is all we have to do. And by one thing that is very nice about these principal component analysis and the eigenvectors is that they are all orthogonal of each other. This means that our new data is then also linearly independent. So this is a nice little bonus of the PCA. And now we can start. So let's import NumPy as NP. And then we create a class PCA. This will get an init with self. And then here we specify the number of components we want to keep, and then we store them here. So we say self.n components equals n components, and we want to find out the eigenvectors, so let's call them self-components here. And this is none in the beginning. And we also want to store the mean later. So let's say self.mean equals none. And then we define our fit method as always. So this will get the data that we want to transform. And then we don't use the predict method. So now we call this transform. So this will transform our data once we fitted it. And this is just the projection. But now let's start with the fit method. So let's say, or again, let's write our approach. So we want to have the mean. Then we calculate the covariance matrix. Then we want to calculate the eigenvectors and values. Eigenvalues. Then we sort our eigenvectors. So sort eigenvectors. And then we store only the first n eigenvectors. So this is what we have to do. And here we have to project our data. So yeah, let's do this. So let's say here we can say self.mean equals, and then we just use the NumPy mean function of our data along the first axis, and then we subtract the mean. So we say x equals x minus self dot mean. So we have to do this because if we look again, then in our formula with the covariance matrix, then always the mean is subtracted. So let's just do this here. And then we calculate the covariance matrix, and this is called cov. And then we simply use the numpy.cov function. So this will do exactly this if we only put in one input here. But now we have to be careful because let's look at our data. So this would be a NumPy ND array where one row, the rows is one sample and one column is one feature vector. But if we have a look at the documentation, then for this function, it's the other way around. So one column is one observation or one sample. So we have to transpose it here. So please double check that for yourself. And then we continue. So now we calculate the eigenvectors and it's the other way around, sorry. Eigenvalues and eigenvectors, and for this we can also use a function in NumPy. So NumPy linealc dot eig, and then we put in our covariance matrix. And here again we have to be careful. If we look at the documentation, then it says that eigenvectors are returned as column vectors. So one column with all one column I here is one eigenvector. And now to do easier calculations, we want to do it the other way around. So we say eigenvectors equals eigenvectors dot transposed, and then we sort them. So for this we say in our sorted indices are NumPy argsort of the eigenvalues now, and we want to have it in decreasing order, so we can use slicing here all the way from start to the end, and we put in a step -1. So this is a nice little trick to reverse a list. And now we have the indices of the sorted eigenvalues in decreasing order. And now we say our sorted eigenvalues equals the eigenvalues with this order, and the same for the eigenvectors equals eigenvectors with these indices. And now we store the first n eigenvectors, so we say self.components, little typo here, self.components equals, and now we can simply say eigenvectors from the start, so from 0 to self.n components. So this is why we transposed it here, so we can easily do this transformation and also this transformation. So this is the fit method, and now we just have to transform it. And now here we must not forget that we should also subtract the mean here. So we say x equals x minus self.mean. This is why we stored it here. And now we can project it and then return it. So we say return NumPy dot, and we project x onto our components. So the dot product with the self.components. But now again we have to be careful here, because here we transposed them, and now again we want a column vector. So here again we have to transpose it. So again, please double check it for yourself. And now we are done. So this is the whole implementation. And now here I've written a little test script that is using the famous iris data set. And then I will create a PCA instance, and I will, so by the way, this will have a dimension of 150 by 4. So we have 105 samples and 4 different features here. And now we only want to keep 2 dimensions. So we put in 2 in our initializer. Then we fit the data, and then we transform it. And then I print the shape of both. And then I will plot them. So now we have a 2D vector, so we can plot it in 2D. So yeah, let's run this and see if this is working. And yeah. So I didn't write Python 3 here, but it worked anyway. So let's test this again. So yeah, here we have our 4D feature vector transformed or projected into 2D, and we see that all the 3 different classes are plotted in a different color. So we can see that we can still have an easy separation of our classes. So yeah, that's very nice. And yeah, that's the PCA. I hope you understood everything, and if you liked it, please subscribe to the channel, and see you next time. Bye. Hi everybody, and welcome to a new machine learning from scratch tutorial. Today we are going to implement the k-means algorithm using only built-in Python modules and NumPy. The goal of the k-means is to cluster a data set into k different clusters, and here we have a unlabeled data set, so we are dealing with an unsupervised learning technique, and each sample should be assigned to the cluster with the nearest mean. So let's have a look at some images to see what this means. So here we have our unlabeled data, and now in this case we want to find 3 different clusters, so it should look like this. And then we assign the labels to the closest cluster, so to the center of the closest cluster. So yeah, this is what we want to do, and how are we going to achieve this? So this is an iterative optimization technique. So first we initialize our cluster centers. So we randomly pick some samples and say these are our first centers. And then we do these 2 steps until we are converged. So first we update our cluster labels, which means we assign the points to the nearest cluster center. And the cluster center is also called centroid. And next we update our centroids. So now we set the center, the new center, to the mean of each cluster. And we iteratively do this until there's no more change. So let's again have a look at the images to see how this is working. So first we have our unlabeled data set. And now we randomly pick 3 centroids. So here I've drawn them. So I hope you can see them. So these are our initial centroids, and now we assign the labels to the of the data to the label of the closest centroid. So this is our first initialization, and now we start optimizing. So now we update our centroids. So we calculate the new mean for each cluster. So I think this centroid will be moved to something like here, and this will maybe be here, and the green centroid will be moved to maybe here. So let's see what's happening. Yeah, so this is the new centroids, and now we update our labels. So now we check which is the closest centroid for each label. So maybe these will become blue and more of these will become orange. So yeah, this is the next step. And now again we update our centroids. So I think this one will further move to the right, and this one will move up here, and this one will maybe stay the same. So yeah, this is the next step. And now again we update the labels. So I think these will become orange now, and these will become blue. And now we are almost done. So maybe here are some slight shifts. So again, update the centroids, then again the labels, then the centroids, then the labels. And now there's no more change. So now we are converged. And yeah, so this is the whole approach. And the only math that we need for this is the Euclidean distance. So I already showed you this in the tutorial about the k-nearest neighbor algorithm. The Euclidean distance between 2 vectors is defined as the square root of the sum over the squared distances. So this is all we need. So now we can start. So let's import NumPy as NP, of course. And then I will set a random seed to, let's say, 42. You don't need this, but I want to reproduce my data later. And since we are using a random initialization, I want to have the same results, or I want to reproduce my results. So I will set a random seed here. And now let's define our Euclidean distance function first. So Euclidean distance of 2 vectors, x1 and x2. So this will be a global function. And here we have to implement the formula that I just showed you, and we can do this in one line. So we say return and NumPy. First we have the square root of, and then we have the sum, NumPy sum. And then we have the sum over all the distances. So we can say x1 minus x2 to the power of 2. So the squared distances. So this is the function. And now we can implement our k-means class. So this will have an init, which has self, and then it will get a k. So this will be the number of clusters, and by default, let's say it's 5. Then it will get a max iters. So this is the maximum number of iterations we want to do for our optimization. And by default, let's say it's 100. And then it will also get a boolean plot steps equals false. So you don't need this, but I'm going to implement an additional function here to plot the different steps like we've just seen. So yeah. So first we set them, or we store them. So we say self.k equals k, self.maxIters equals maxIters, and self.plotSteps equals plotSteps. And now we create our empty clusters and centroids. So self.clusters equals, and now here we want to be careful because this is important. So this is a list of lists. So a list of sample indices for each cluster. And in the beginning, each cluster has an empty list. So we say, and we use list comprehension and then say we have an empty list for underscore in range self.k. So for each cluster, we initialize an empty list. And then we say our self.centroids equals, and this will also be an empty list. And here we are going to store the feature vectors, or the mean feature vector for each cluster. So mean feature vector for each cluster. So here we are having actual samples, and here we just stored the indices. So this is important. And now we can continue. So now usually we would implement a fit and a predict method, but since we are having a unsupervised learning technique here, we don't have any labeled data, we just have to implement the predict method. So, and we don't need the fit method. So let's define our predict method with self and x. And here, first, let's store our data, self x equals x, and then the dimensions, so self number of samples and self dot number of features equals x dot shape, because we need this later. And as always, this is a NumPy ND array. And so yeah, so now let's do the steps we just talked about. So first we have to initialize our centroids, and then we do a optimization. So here we can say for underscore in range self dot max iters, and now here in our loop, first we update our clusters. So let's say update clusters, and then we update the centroids, and then we check for convergence, check if converged, and if so, then we break. And at the end we want to classify the samples as the index of their clusters. So here we say return cluster labels. So this is what we have to do. So now let's start. So let's say we want to initialize our centroids. So we want to randomly pick some samples. So let's say random sample indices equals, and now we use list comprehension. So, or no, sorry, here I can use numpy dot random dot choice, and this will get self dot number of samples and self dot k, and we also have to say replace equals false because we don't want to pick the same indices twice. So this will be an array of size self.k, and for each entry it will pick a random choice between 0 and the number of samples. And now we assign the according sample that belongs to this index to our centroid. So we say self.centroid equals, and now here we use list comprehension, so we say self.x of the current index for index in random sample indices. So this is the initialization of our centroids, and now we can do the optimization. So first we update our clusters. So we say self.clusters equals self.create clusters, and this will get self.centroids. So this is a helper function, create clusters, that we are going to implement now. So define create clusters with self and the centroids. So here we assign the samples to the closest centroids to create our clusters. So first we have an empty list of lists for our clusters. And now we iterate over our data. So we say for index and sample in enumerate self.x. So this enumerate function will give us the current index and the current sample. Now we want to get the closest centroid, and we want to have the index of this. So we say centroid index equals self.closest centroid, and this will get the current sample, and then it will get the centroid. So this will be another helper function that we will create in a second. But now let's continue here. So when we have the centroid index, we append, or we take the current cluster, so the clusters of this centroid index, and then we append the current index. So we put the current sample index in the closest cluster, and then we return our clusters. So this is how we create our clusters, and now we need the define closest centroid function, which gets self and a sample and the centroids. And here we calculate the distances of the current sample to each centroid, and then want to get the centroid or the index of the centroid which has the closest distance. So let's calculate all the distances with list comprehension. So here we use the Euclidean distance function that we already have. So the Euclidean distance of a sample and of each centroid point. So point for point in centroids. And then we have all the distances here, and now we want to see which is the minimum, or the index with the minimum distance. So we can use NumPy argmin here. So we say closest index equals NumPy argmin of this distances, and then we simply return it. So return the closest index. So now we have this, and now we created our clusters, and now we can continue with our optimization. So here we update our centroids as the next steps, but before we want to store the centroid. So let's say centroids olds equals self.centroids, so that we can check for convergence later. And then we say self.centroids equals self.get centroids of this, and this will get self clusters. So this is another function. This will assign the mean value of the clusters to the centroids. So for each cluster, we now calculate the mean. So let's define this. Define get centroids, which gets self and the clusters. So here we initialize our centroids with zeros in the beginning. So let's say centroids equals NumPy zeros, and this will be of size self k and self.n features, and here this should be a tuple, so we have to be careful here. So for each cluster we will store the feature vector, so that's why it has to have these dimensions. And now we iterate over the clusters. So we say for cluster index and cluster in enumerate clusters, and then we calculate the cluster mean. So cluster mean equals NumPy mean of our self.x of this cluster indices, and this should be along the first axis. So again, let's have a look at what this means. So as I said, our clusters is a list of lists. So if we have just the current cluster, then this is a list, and this is a list of the indices that are in this cluster. So if we call self.x with this indices, then it will only return the samples that are in the current clusters, in the current cluster, and then we calculate the mean. So this is what's going to happen here. And now once we have our mean, we assign it to the current cluster, so to the current centroid. So we say centroids of the current cluster index equals cluster mean, and then we are done and can return the centroids. So yeah, so now we have our new centroids, and now we check if we are converged. So we say if self dot is converged, then we will break, so we can stop here, and this will get the centroids old and the new ones, so self.centroids, and this is another helper function. This will simply calculate the distances between each old and new centroids for all the centroids and check if this is 0. So define is converged self and centroids old and new centroids. So again, we calculate the distances with list comprehension, distances equals, and here we calculate the Euclidean distance of centroids old of I, so the current centroid vector, and the new one, so centroids I for I in range self dot k. So for each cluster, it will look at the old and the new centroid vector and calculate the Euclidean distance and store it in this list. And then we can return sum of distances equals 0. So this is a built-in function that will iterate over this entries and calculate or sum it up. And so if this is 0, then there is no more change in our centroids. So we say it is converged. So yeah, so now we have this. And now we want to return the cluster labels. So let's say return self dot get cluster labels. And this will get self dot clusters. So here for each sample we will get the label of the cluster it was assigned to. So let's create this right here. So define get cluster labels with self and the clusters. And so first we say our labels equals a NumPy empty array of size self.number of samples. So for each sample we want to return which is the cluster it was assigned to. But be careful here, because these labels are not the actual labels of our data, because we don't know them. So this is just the index of the cluster it was assigned to. So yeah, so now we iterate over the clusters. So for cluster index and also cluster in enumerate clusters. And then we iterate over the current cluster. So for sample index in cluster. So again, this is a list of lists, and each cluster has a list, has all the sample indices of the samples that are in this cluster. So for each sample index in this current cluster, we say labels of the sample index equals the current cluster index, and then we return our labels. And now we are done. So one more thing that I want to implement, but you don't need this, is to have a plot function. So define plot and self. And here we are going to use matplotlib. So I can say import matplotlib.pyplot as plt. And I'm not going to explain the details here, but if you want to see more tutorials about matplotlib, then please leave some comments. So let's implement the plot method. So here I simply want to plot the data and to which cluster it belongs, and then also the centroids. So let's create our figure. So fig ax equals plt.subplots, and let's give this a fig size of size, let's say 12 by 8. And then we iterate over our clusters. So for I and index in cell in enumerate self.clusters. And now we get the current point. So point equals self.x of the index, but we have to transpose it here. And now we scatter the point. So ax.scatter, and here I unpack the point. And now, so this will plot all the points, and for each cluster it will use a different color. And now we plot all the centroids. So for point in self.centroids, ax.scatter, and again we unfold our point, and then we say marker equals x, so it has a marker sign, and color equals black, and line width equals 2. So, and then we have to say plt.show, of course. And so this is the plot function. And now during our optimization, if we set plot steps to true, then we want to plot after we updated our clusters. So we say if self.plot steps, then self.plot. And again, we also want to plot after we updated our centroids. So we put it right here. And now we are done. So now let's run this, and I hope that everything is working. So let's clear this and run our script. And oh, I missed a comma here, line 37. Update centroids old equals the current ones. So again, let's try this, and now it's working. So here we have, I created a data set with 4 different clusters, and we can see that it correctly could identify them. So let's set plot steps to true, and don't plot it at the end. And now let's run it again to see the different steps. So here, this is after our initialization. So we randomly picked some samples and said these are our first centroids. So maybe the initialization is not very good here, but it could find out the clusters correctly later. So let's see what's happening. So now we are, then we are starting to optimize. So now in the next step, we are calculating the new centroids. So I think the centroid of the blue cluster is moving to maybe over here, and the orange centroid is moving to down here. So let's look at the next step. So yeah, and now we are updating the labels. So I think these here are no longer orange, but red and green. So yeah, and also some of them are now red. And now we update our centroids again. So I think this will further move over here. This will move down here, and these will move a little bit. So yeah. And now we again update our labels. So I think more of them will become red, and more of them here will become green. And now again we update our centroids. So I think this will further move over here. The red centroid will move over here. This is already good, and the green one moves over here, I think. So yep, that's that. And now again we update the labels. Now again the centroids and the labels, and now I think we are converged. So yeah, this is how the k-means works, and I hope you understood everything. And if you liked it, please subscribe to the channel, and see you next time. Bye. Hey guys, welcome to another machine learning from scratch tutorial. Today we are going to implement the AdaBoost algorithm using only NumPy and built-in Python modules. AdaBoost uses the boosting approach, which follows the simple idea to combine multiple weak classifier into one strong classifier. And this approach works really well in practice. So let's start with a theory before we jump to the code. So let's have a look at this 2D example here to understand the concept. So here we have our samples with only two different features on the x-axis and on the y-axis. And now the first classifier makes a split based on the y-axis in this example. So it draws a horizontal decision line at some threshold, so the dashed line that we can see here. And we can see that some predictions are correct, but we also have misclassifications. And now with these misclassifications, we can then calculate a performance measure, so the accuracy for this classifier. And with this measure, we calculate and update weights for all training samples. And now the second classifier comes in and it uses these weights and finds a different and possibly better decision boundary. So the second classifier in this example here chooses a feature on the x-axis and draws a vertical line. And then again, we calculate the performance and update the weights. And then we repeat the step for as many classifiers as we want. And then here at the very end, we have all the different decision lines, and we also have all the different classifier performances. And then we combine all our classifiers so we can make a weighted sum with the calculated performances. And this allows us to draw the perfect decision line that we can see here, which can be more complex than a simple linear decision line. And the idea with the weighted sum here at the end means that the better the classifier is, the more impact it has for the final outcome. So this is basically the concept. And now let's look at all the different steps and also the math behind this in detail. So the first thing that we need is a weak classifier, and this is also called weak learner. So a weak learner is always a very simple classifier, and in the case of the AdaBoost, we use a so-called decision stump for this. So a decision stump is basically a decision tree with only one split, so what we can see here. So we look at only one feature of our samples and only at one threshold. And then based on if our feature value is greater or smaller than the threshold, we say that it is class -1 or class +1. So this is the decision stump. And then we need the formula for the error. So the very first time during our iteration, the error is calculated as the number of misclassifications divided by the total number of samples. And this is the natural approach for the error. So if we have a look at our example again, then we can see that we have 10 samples in this case. And in the first classifier, we have 3 misclassifications. So this means that our error rate is 0.3 or 30%. So this is the first time, but the next time we also want to take into account the weights. So if a sample was misclassified, we give it a higher weight for the next iteration. And this means that our formula is then calculated as the sum over the weights for all misclassifications. And if our error is greater than 0.5, we simply flip the error. So we flip all decisions, and we also flip our error. So it is then 1 minus the error. So this is the error, and now we need the weights. So the weights are initially set to 1 over n for each sample. And this also matches the error calculation in the first step. So if we say we calculate the error as the sum over all misclassified weights, and we also say that each weight is 1 over n in the beginning, then it is equal to the number of misclassifications divided by the number of samples, like here. So yeah, that's why the initial weights are 1 over n for each sample. And then we also need the update rule that is defined here. So we have the old weight times the exponential function of minus alpha times the actual y times h of x, where h of x is our prediction and alpha is the accuracy of the classifier. So if this is -1, we have a misclassification, and if this is +1 here, then we have a correct classification. And this whole formula basically makes sure that misclassified samples have a higher impact for the next classifier. So yeah, this is what you should remember from the weights. And now the performance. So we need to calculate the performance or alpha for each classifier. And we can do this, we need this for the final prediction then. And the formula for the performance is calculated as this. So it's 0.5 times the log of 1 minus the error divided by the error. So let me make this a little bit larger for you. So this is the performance. And our error is always between 0 and 1. So I plotted alpha for different errors in this range here. And we can see that it is equally distributed somewhere between a positive value here and a negative value here. So with a low error, we have a high positive value. And with a high error here, close to 1, we have a high negative value. But since we are flipping the decision then, this will then be correct classifications again with a high contribution to the negative side. So the side here where the class is -1. So this is the concept of the alpha. And now we need the prediction. So now if we have understood all of this, then the final prediction is very easy to understand. So we just choose the sign here, the sign of the sum over all predictions, where we weigh each prediction with the performance of the classifier. So alpha times the prediction here. So the better our classifier, the more impact it has for the final prediction. And the better the classifier, the more it points into the negative or positive side. And then we take the better side as prediction for our class. So yeah, that's the concept of the prediction. And it can be a bit confusing with the different formulas and the side flipping, but the basic concept is not so difficult. And let's summarize all the different training steps that we must do in the code. So first of all, we initialize our weights for each sample and set the value to 1 over n. Then we choose the number of weak learners we want, and then we iterate over this, and then we train each decision stump. So we do a greedy search to find the best split feature and the best split threshold. Then we calculate the error for this decision stump. So this is with the formula, the sum over the misclassified weights. Then we also flip the error and the decision if it is greater than 0.5. Then we calculate the alpha with the formula. And then we need the predictions. And then with the predictions and the alpha, we can then calculate, we can then update the weights. So this is what we must do in the code now. And yeah, I promise you that since now that we have all the formulas and all the training steps here, the implementation is pretty straightforward and should not be so hard. So let's jump to the code. So the first thing we do is import NumPy. So import NumPy as NP, and this is the only module that we're gonna need. And now we create a class for the decision stumps. So class decision stump. And this gets an init. So define an init. And this only has self. And here we want to store a couple of things. So the first thing that we want to store is the so-called polarity. So self.polarity equals 1. And this tells us if the sample should be classified or as -1 or +1 for the given threshold. So if we want to look at the right or the left side, and this is needed because if we want to flip the error, then we also must flip the polarity. So this gets clearer in a second. And now the second thing that we want to store here is the feature index. So self.feature index equals none in the beginning. And we also want to store the threshold, so the split threshold. Self.threshold equals none in the beginning. And we also want to store the a variable for the performance, so the alpha. So we say self.alpha equals none. So this is the things that we want to store. And then we also define a predict method for the decision stump. So we say define predict, and it gets self and it gets x, so the samples that it should predict. And now what we want to do here is simply look at only one feature of this sample, and then compare it with the threshold and say if it's smaller then it's -1 and otherwise it's +1. So that's the whole concept of the decision stump. So let's do this. So let's say the number of samples equals x.shape 0. And then let's get only this feature. So let's say x column equals x, and then we can use a colon. So we still want all the samples, but only this feature index that we calculate later during the training. So self.feature index. And now we make our predictions. So we say predictions equals, and by default we say this is 1. So let's say NumPy ones with the size of the number of samples. And then we must check the polarity. So we say if self.polarity equals 1. So this is the default case. Then we say that all the predictions that are smaller, where the feature vector is smaller than the threshold, then it's -1. So let's say predictions, and then at these indexes where x column is smaller than self.threshold, then these predictions are -1. And in the other case, else, so if our polarity is -1, then we want to do it exactly the other way around. So let me copy this. But we want to say if the x value is greater than our threshold, then these are the -1 predictions. So yeah, this is all that the decision stump is doing, and then we can return the predictions. So this is the class for the decision stump, and now we need a class for the actual AdaBoost algorithm. So let's say class AdaBoost, and let's make this a small letter. And now we need a init first, so define a init, and this gets self, and the only parameter it gets is the number of classifiers that we want. So let's say nclf equals 5 by default, and then in the init we store these numbers. So we say self.nclf equals the number of classifier. And then, as always, we want to implement the fit and the predict method. So let's start with the fit method. So let's say define fit, and it has self, and it has x and y, so the training samples and the labels. And now the first thing we do is to get the shape of this vector, so the number of samples and also the number of features equals x.shape. And then we want to initialize our weights, so init the weights. And as I said, all the weights for each sample is set to 1 over n in the beginning. So let's say w equals NumPy, and then we can use a method from NumPy that is called full. So NumPy full, and it gets the size number of samples, and then it gets an initial value, and here we say 1 over the number of samples. So this sets each value to this calculated value, and then this is our initialization. And now let's iterate through all the classifiers and do the training. So first we create a list where we want to store all the classifiers. So let's say self.clfs. And this is an empty list in the beginning. And now let's do the iteration. So let's say for underscore in range And here we have the number of classifiers that we specify. So self.nCLF. And now what we want to do here is we want to do the greedy search. So we want to iterate over all the features and all the thresholds. So this is similar to the decision tree implementation that I did in another tutorial, and I recommend that you check that out too. So we want to do a similar thing here. So first we create our classifier. So let's say CLF equals decision stump. And now let's define a min error in the beginning. So we want to find the best feature value, the split feature and the split threshold, where this error then is minimum. So in the beginning, we just say this is float inf. So this is a very high number. And now let's iterate over all the features. So let's say for feature I in the range of, and here we have the number of features that we got in the beginning. And then we want to get only this feature. So let's say X column. So this is similar to what we did here. So we can do the same thing and say X column equals this. So all the samples, but only this feature index. So I called it feature I in this case. And then we want to get only the unique values, and these are our thresholds. So let's say thresholds equals NumPy dot unique, and here the unique values of our column, so X column. And now we iterate over all the thresholds. So let's say for threshold in thresholds. And now what we want to do is we want to predict with the polarity 1 first, and then calculate the error with the formulas that I showed you in the beginning. So let's say our polarity equals 1. And then let's do the predictions. So predictions equals, and this is similar to what we did here. So in the beginning, it's just 1. And then we use this formula here. So since our polarity is 1, we have to compare it by saying if it's smaller than our threshold. So predictions where our column value, our feature value is smaller than our threshold, then there our predictions are -1. So now we predicted all the samples, and now we want to calculate the error. And as I said, the error is the sum over the weights of the misclassified samples. So let's get the misclassified weights. So let's say misclassified equals W, and the W where our Y, our training labels, is not equal to the predictions that we just did. So these are the misclassified weights. And now we want to simply calculate the sum over these weights. So error equals the sum over this misclassified weight. So this is the error. And now we also want to flip our error if it is greater than 0.5. So we say if error is greater than 0.5, we simply say that our new error equals 1 minus the error. And then we also flip the polarity. So we say P equals -1. So now we have our error, and now we check if our error is smaller than the min error. So let's say if error is smaller than the min error, then this is our new min error. So we say min error equals error. And now this is the best current fit for our decision stump. So we want to store this. So we say CLF.polarity equals P, and only P. And we also want to store the threshold and the feature. So CLF.threshold equals the current threshold. and clf.feature index equals feature I. And yeah, so this is the whole training loop for a classifier. And now when we are done with both for loops, what we want to do here is, I have to check if I'm on the right indent. So now what we have to do is to calculate the performance. So calculate alpha. So we say, and clf.alpha equals, and then we need this formula here. So 0.5 times the log of 1 minus the error divided by the error. And we also use a little epsilon so that we don't divide by 0. So let's say eps equals this small value. And this is our epsilon. And now let's use the formula. So 0.5 times NumPy dot the log. And here we have 1 minus the error. And then divided by, here let's say error plus our epsilon. And let's wrap this in another parenthesis. So this one. And let me check if this is correct. So let's do another one around this one here. And then this should be fine. So this is our alpha, and now we want to update the weights, and for this we also need the predictions. So let's check the formula again. So this is the old weight times the exponential function of minus the alpha that we just calculated times the actual predictions, or the actual labels times the predictions, and then we normalize it. So this is the formula that we need. So let's write this here. And let's first get the predictions. So we can say predictions equals, and we already implemented this. So we can simply say clf.predict x, x, yeah. So we get the column up here. So we can put the whole x here. And now we have the predictions, and now we can use them and update the weights. So we say our weights is multiplied equals, and then we say NumPy x, so the exponential function, and then minus clf.alpha times, and here the actual labels, and then times the predictions. So times predictions. So, and then we want to normalize it. So we divide it by the sum over this weight. So we say W divided equals, and then here we say NumPy dot sum W. And now we are done. So we updated our weights, and then we want to store this classifier. So we want to save it. So we say self.clfs.append the current classifier. So we append clf. And now we are done with the fit method. So this is the whole training of our AdaBoost classifier. And now what we also need is, of course, we want to have the predict method. So let's implement this down here. So let's say define predict, and here it gets self, and it also gets x. And now this is the formula that I showed you here. So we look at the sign of the sum, and here we multiply each alpha with the prediction, yeah. So let's do this. So let's say clf.preds equals, and here we use list comprehension, and then we do this for each of the classifiers. So we say clf.alpha times, and here we use the prediction clf.predict, and here we want to predict x, and we want to do this for each of the stored classifiers. So we say for clf in self.clfs. So these are all the predictions in the sum, and now we need to calculate the sum. So we say y pred equals, and then numpy dot sum. And here we say CLF preds and along the axis 0. So now we have the sum, and now the very last thing that we need to do is to look at the sign. So we say y pred equals numpy dot sign of this y pred. And this is our final prediction, and then we can return this. So let's return y pred. And now we should be done. So now we have the fit method and the predict method. And now here I've already written a little test script. So here I import this class that we just created. So from AdaBoost, import AdaBoost. Then I also have a accuracy measure here. And then in this example, we load the breast cancer data set from the sklearn datasets. And then the important thing that we must do here is to set all the labels that are 0 at the moment to -1, because AdaBoost needs the labels as -1 and +1. And then we do a train test split as always. And then here we create a AdaBoost classifier, and in this case I put in 5 classifier. Then we call the fit method, and then we call the predict method, and then we calculate the accuracy. So this is the test script. So let's run this and hope that everything's working. So let's say Python AdaBoost test, it's called, and hit enter. And it's running and it's calculating. And I hope that it's working, and now we are done. So yeah, so here we have a accuracy, and it's pretty good in this example. So we have 0.94. So we see that it's working. And yeah, I hope you enjoyed this tutorial, and see you next time. Bye. Hey guys, welcome to a new machine learning from scratch tutorial. Today we are going to implement the linear discriminant analysis algorithm, or short LDA, using only Python and NumPy. LDA is a dimensionality reduction technique and a popular pre-processing step in machine learning pipelines. LDA is similar to the PCA technique that I already showed in a previous tutorial. The approach and the implementation of PCA and LDA have a lot in common, so I highly recommend that you watch this video first. And now let's talk quickly about the concept of LDA before we jump to the code. So the goal, as I already said, is feature reduction. So we want to project our data sets onto a lower dimensional space and find a good class separation. So here we have the difference between PCA and LDA. So in PCA, or principal component analysis, we want to find new axes onto which we project our data such that we maximize the variance on the new axis. And now in LDA, the big difference is that we know the feature labels. So this is a supervised technique. And here we want to find new axes such that the class separation is maximized. So if we have a look at this image here, we have 2 different classes, and then we could project our data either onto the y-axis or onto the x-axis. And now in this case, the y-axis would not be a good choice, but the x-axis is a good choice because here we still have a good class separation. So this is the concept of the LDA. And here I listed the differences again between PCA and LDA. So in PCA, again, we want to find the component axes that maximize the variance of our data. And in LDA, we want to do this too. So within one class, within the green field and within the blue field, we still want to have a good variance between the single features. But also additionally, here we are interested in the axes that maximize the separation between multiple classes. So this difference here basically should be maximized in the new axis. And yeah, LDA is supervised learning, so we know our labels, and PCA is unsupervised. So this is an important thing that we should remember. And now let's jump to the math. Here we have the so-called scatter matrix, and we have two different scatter matrices, the within class scatter and the between class scatter. This basically represents what I was talking about here. So the within class scatter makes sure that our features within one class are good separated, and the between class scatter makes sure that the two or all the classes are good separated. And if we translate this to the math, then we have to deal with the mean values and the variances. So the formula of the within class scatter is the sum over the scatters, and each scatter of one class is the sum over, and then the feature value minus the mean value of all the features only in this class, and then times the same transposed, and then we sum over all the features in this class. So this is basically the same as in the PCA algorithm, where we want to compute the covariance matrix. So this is almost the same formula as for the covariance matrix, except that we don't have the scaling at the beginning. So this is the within class scatter, and then the between class scatter. Here the formula is the sum over all the classes, and then for each class we have the number of features in this class, the number of labels in this class, and then times the mean value. So this x bar is the mean value of the features in this class minus the mean value in total, so the total mean of all features, and then times the same transposed. So these are the two matrices that we have to compute, and then we calculate the inverse of the within class scatter and multiply that with the between class scatter. And this is our eigenvalue and eigenvector problem that we have to solve. So this is the same as in the PCA. I will not go into detail again, so please make sure that you know what eigenvalues and eigenvectors are. So basically what we have to do then is, for this formula, we have to calculate the eigenvalues, and then so let's have a look at the whole approach again here. So here I summarized it. So first we want to calculate the between class scatter and the within class scatter. Then here we calculate the inverse of the within class scatter and multiply it with the between class scatter. Then of this we calculate the eigenvectors and eigenvalues. Then we sort the eigenvectors according to their eigenvalues in decreasing order. And then we choose only the first k eigenvectors that we specified, so only the k dimensions that we want to keep. And these eigenvectors are called the linear discriminants. That's why it has this name. And then we transform our original data points onto this k dimensions. And this transformation is basically just a projection with the dot products. So this whole approach is the same as in the PCA algorithm, except that we have to solve the eigenvalue and eigenvector problem for a different formula in the beginning. So that's the approach, and now let's jump to the code. So of course we import NumPy as NP, and then we define our class, and let's call this LDA. And here we define our init, which has self, and it also gets the number of components that we want to keep. And here we simply store that, so we say self n components equals n components. And we also create a variable that we call self.linear discriminants, and this is none in the beginning. And here we want to store the eigenvectors that we compute, And then we define our fit method. So here we have self, and then we have x, and we also have y, because remember, this is a supervised technique. And then we also implement not the predict method, but we call it transform. So transform. This is the same as in the PCA. And here we want to get the new features that we want to project. So let's implement the fit method. So here first what we want to get is the number of features, and we get this by saying x.shape and then the index 1. So index 0 is the number of samples, and here we only want to have the number of features. Then we also want to get all the different class labels. So let's call this class labels, and this is equal to NumPy, and then we can apply the unique function of y. So this will only return the unique values in our labels as a list. And now we want to calculate the two scatter matrices. So S underscore W for the within class scatter and S underscore B for the between class. So let's do this. And first of all, I want to calculate the mean of all our samples, because we need this later for one of the formulas. So we say mean over all equals NumPy dot mean of x, and then along the axis 0. And then let's initialize our two matrices. So we say SW or S underscore W equals NumPy 0. So we want to fill this with zeros, and we want to give this a size of the number of features times the number of features. And the same thing with the between class scatter. So we initialize this with zeros. So later we want to test this, for example, with the features of the iris data set. So this has a size of this has, I think it's 150 samples and 4 features. So this has size 4 times 4, and this is the same, 4 times 4. And now we have to apply the two formulas. So we have to sum over all the classes and then apply these two formulas. So we can do this in one for loop. So we say for C in class labels that we computed, and then what we want to get first is we want to get only the samples of this class. So we say xc equals x where y equals c, so where we have this label in the current iteration. And then we want to get the mean from these features, mean c equals, and this is NumPy dot mean of xc along axis 0. So the same as we are doing it here, but only for the features in this class. And then let's have a look at the within class formula. So here we have our feature, and then subtract the mean value, and then this is basically the dot product times the transposed. And so let's do this. So here we say our S within plus equals, because here we sum over all the classes. So plus equals, and then here we say xc minus mean c, and then I transpose this and calculate the dot product times the same as we are doing it here. So here we have to be careful. So if we have a look at the formula again, then we see that I have the transpose term at the end, and here I transposed the first term. And this is because here we are having one more sum, so we do this for all the samples in this class. And here we do this sum in one operation with the dot product, so with our NumPy operation. And then we have to be careful with the sizes. So what we want at the end again is a 4 times 4 matrix, like here, because we append this to these matrices. And in the beginning, our xc and our mean c has the size number of samples in this class times 4. So we have to turn this around. So we have to say this is size 4 times number of samples in this class. Because when we multiply this, or when we compute the dot product with this one here, which is not transposed, so here we have the number of samples in this class times 4, and then if we multiply this, then we get a matrix of the size 4 times 4. So these are basic rules of matrix operations. Be sure that you understand this. So the last dimension of the first matrix must match the first dimension of the second matrix, and then the final output size is composed of these two sizes. So this is why we have to transpose the first term here. So this might be a little bit confusing. Make sure to double check this for yourself. And then we have the within class scatter. And now for the between class scatter, what we want to get is the number of samples in this class. So we get this nc by saying this is equal to xc.shape. And here we want to have the index 0 because we want to have the number of samples. And then here again, we have to be careful because we have to reshape our vector. So let's say our mean diff. Let's have a look at the formula again. Here we calculate the mean of this class minus the total mean. So let's do this. So this is, let's say, we have the mean of this class minus the mean overall. And this is only one dimensional, but we want to, so this is, if we have a look at the shape, then this would say 4, nothing, but we want to have it to be 4 by 1. So we have to say reshape and then the number of features times or by 1. And this is because, again, if we have a look at the final multiplication, so the same way as we are doing it here, we want to have a matrix of size 4 by 1 and multiply it with a matrix of 1 by 4. So this is basically 4 by 1 transposed. And then we get a 4 by 4 output. So this is why we have to apply the reshape here. And then we say SB plus equals, and then here we have the number of samples in this class times, and here we have the mean diff dot the mean diff transposed. And these are both of our matrices. So we finally have the matrices now. And now, as I said, we have to get the inverse of the within class scatter and then multiply it with the between class scatter. So we get the inverse also with NumPy by saying NumPy lin alg dot inf of SW. And then dot, we multiply it with the between class scatter. And let's call this A and store this in this matrix. And then for this, we have to solve the eigenvalue and eigenvector problem. So we have to calculate the eigenvalues and eigenvectors. And now the following code is exactly the same as in the PCA algorithm. So please check that. So we get the eigenvalues and the eigenvectors by saying this is NumPy linalg.eig of A. And then we sort the eigenvectors and the eigenvalues. And for this, the same as we are doing it in the PCA algorithm. So we transpose the eigenvectors by saying eigenvectors equals eigenvectors.t. So this makes the calculation easier. And then we sort the eigenvalues. So we say indices equals numpy.argsort of, and here we say the eigenvalues, and to make it a little bit nicer, we actually want the absolute value of the eigenvalues. And then we want to sort this in decreasing order, so we use list slicing and use this little trick from start to end with a step of -1. So this will turn the indices around, and then we have it in decreasing order. So now let's get our eigenvalues in decreasing order by saying eigenvalues equals eigenvalues of these indices, and the same with the eigenvectors. So eigenvectors equals eigenvectors of these indices. And then we want to store only the first n eigenvectors, and we store this in our linear discriminants that we have here. So we say self dot linear discriminants equals eigenvectors, and then from the start, so the biggest eigenvector with the biggest or the highest eigenvalue, and then to self dot number of components that we specified. So this is the number of dimensions that we keep. And now we are finally done with the fit method. So this is the whole fit method. And then in the transform, the only thing that we do here is we project our data onto this new components. And the transformation is nothing else than the dot product. So we can write this in one line and return numpy dot. And then we project our data onto the self dot linear discriminants. And since we are transposing it here, we have to transpose it again here. And then we are done. So this is again the same as in the PCA. Please double check this for yourself. And now we are done, and now we can run the script. So here I have a little test script, and this is basically the same as in the PCA tests. The only thing that I exchanged here is instead of PCA, we create the LDA and want to keep two components, and then we call the fit and the transform, and we do this for the iris data set. And then I plot the new labels that are projected onto the new 2 dimensions. So let's run this. So let's say Python LDA underscore tests.py and hope that everything's working. And yeah, so here we see our transposed features in only 2 dimensions now, and we see that the classes are very good separated. So here we have the 3 different iris classes, and we see that this is working. So our LDA feature reduction method works. And yeah, please again compare this with the PCA algorithm. And I hope you enjoyed this tutorial. If you like this, then please subscribe to the channel, and see you next time. Bye. Hey guys, welcome to another machine learning tutorial. So in all my previous machine learning examples, I used available data directly from the sklearn datasets module. And a lot of people have asked me how they should load their data if they have their own data sets. So today I want to show you how you load the data from a file. I will show you 4 different ways, one with pure Python, 2 with NumPy, and 1 with the pandas library. I will also show you what you should do with headers, missing data, and how to get the correct data type. So please make sure to watch all the way to the end. And now in this tutorial, I'm going to use the spam-based data set. So if we Google this, then the first entry leads us to this site. And this is a popular website to get machine learning data sets. And in this spam-based data set, we want to classify emails as spam or no spam. So we can then go to the download folder and load the spam-based.data. And I already did this, so I have this here. And this is in CSV format, so comma separated values. And usually the ending here would be .csv, but here it's .data, which is fine too. So let's start and let me show you how we can load this. So first, let's load this with pure Python and the CSV module. So we can import CSV. This is already built in Python. Then let's specify our file name equals. So let's have a look at this again. This is called spam-based data. So let's call this spam-based.data. And now we say with open our file name in read mode as f. And then we say our data equals, and then we can use the CSV module and call the reader, and here we have to give it our f and also the limiter, so the values that separates all the data, and in this case it's a comma, and this will give us an iterator, and then we can use the list method to convert this to a list. And now we have the data in a list, so let's convert this to a NumPy array. So let's import NumPy as NP, and then down here we say our data equals a NumPy array from the data, and then for example we can print the data.shape. So let's run this, and then we see that it worked. And if we have a look at the website, then we can see here the number of samples is 4,601 and the number of features is 57. So here we have 4,601 and 58, and this is because our data holds both the features and the class label right now. So now here in this case, the class label is the very last column. So the next thing we want to do is to split our list here into features and class labels. So for this, let's get the shape. So let's say number of samples and the number of features equals data.shape. And then we use list slicing. So first thing we want to do is to decrease this by 1. So let's say number of features minus equals 1 because we only have 57. And then we use list slicing. So we say x equals data, and then we say colon. So we want all the rows. And for the columns, we want to start at column 0 and all the way to the number of features. And this last column is excluded. So this will only hold the features. And for the y, this is data. And again, we want all the rows, but only the last column. So now we have splitted this, and now, for example, if we print x.shape and y.shape, and if we run this, then we see that this worked, and now we have it in the correct format. For example, now we can put it or give it to our classifier for the fit method and start our training. So this is the first way that I wanted to show you. However, I would not recommend this because this is usually slower and also needs more code than the other methods, which I'm going to show you now. But you should still know how to load a file manually. So let's forget this now and let's delete this. And now let me show you how we can do this in NumPy. So in NumPy, we can do this with only one line. So we can say data equals NumPy. And then we use a method that is called load_txt, and this also needs the file name, and the delimiter equals a comma, and this is all we need. So now if we run this, then we see that it worked too, and this is much simpler and also faster. So this is the first method that we can use with NumPy. However, there's an even better one which I would recommend. So this is data equals NumPy, and the second method is called gen from txt, and this also needs the file name, and the delimiter equals the comma. And now if you run this, then we see that this worked too. So this is my preferred method with NumPy. And it basically does the same as this one, but it offers a little bit more options for the parameters. For example, here we can deal with missing data, which I want to show you in a second. So yeah, so this is the function with NumPy. And now as a last thing, I want to show you how we can do this with pandas. So if you're already familiar with pandas, then you can use this too. And here we have a function that is called read CSV. So we say data frame, because in pandas we usually deal or call this data frame. And then we say pd dot read underscore CSV, and again our file name. And we could also give it the delimiter equals the comma, and then we have it as a data frame. And then what we can do is to convert this to a NumPy. So we can say data equals data frame to NumPy And then we can do the same as we are doing here. For example, we can split this into X and Y. And now if we run this, then we see that this worked too. But here we now have one row too less. And this is because here we have to be careful, because pandas tries to read a header, and in this case we don't have a header, so we have to say header equals none. And then if we load this, then we see that it is correct again. So this is how we can use pandas. Both are fine, so I would recommend using this if you only want to use NumPy. And if you are familiar with pandas, then I would use this one, because this is even more options and it's also a little bit faster. So yeah, so that's how you can load this. And now let's talk about the data type, the header, and missing data. So one thing that is good practice is to already specify the data type if you know it. So for example, here we can give the argument data type equals, for example, NumPy float 32. And down here we can do the same thing for the pandas function. So now if we run this, then we see this work too. And for example, we can print the type of data too. Then we see, here we see it's only one NumPy array. Let's print the type of data, let's say 0, 0, then we should see that it is in NumPy float 32. And it's good practice to always specify this if you know it. So if you know the data, then put it here, because otherwise the function has to figure out the data type for itself, and this usually takes a little bit more time, and it can also be wrong. And yeah, so some algorithms, some classifier expect this as float, or I think the most of them expect this as float, so that's what I would recommend to do here. If you don't put it in here and want to convert it later, by the way, then you can still do this by saying data equals NumPy as array, and then you put in the data, and then as data type equals, and then here your float 32. Yeah, so that's what you can do with the data type. And now let's talk about a header. So in this case, we don't have a header, but let's say in our file we have a header where we, for example, have the feature descriptions, feature 1, feature 2, and so on. So during the loading, we don't want this, of course. And then what we can do here is, first of all, let's run this and see what happens. And then we get an error because our functions cannot figure out the first row. So what we can do here is we can simply skip this. So for the gen from text method, we need to say skip header, and then the number of rows we want to skip. So in this case, it's 1. And the same for the pandas function, but here we have to be careful because here the argument is called skip rows equals 1. And now if we run this, then this worked again, and we again have the correct shape, and it skipped the header. So this is what you should do if you have a header here. And now as a last thing, I want to talk about missing values. So a lot of time, for example, there are missing values. For example, here we just have a comma and then no entry. And so if we run this, then let's print, for example, let's print X, and then in the first row, let's print the features 0 to 5. And down here the same. So now if you run this, we see we have a NaN. So this stands for not a number. And these functions can figure this out on their own. So if it is empty, or I think if there is a dash or a NaN, so then they can automatically see that this is not a number. But sometimes you also have a string here, which doesn't make sense. And now if I try to run this, then this should produce an error because it cannot figure out the string here, because you said all these should be floats. So what you can then do here is we can specify additional missing values by saying missing values equals, and then here you put in a list, and here we can put in hello. And for the pandas function, the argument is NA values, and then here you have to use a list. So I recommend to check out the documentation whenever you need the arguments. You don't have to memorize this. So here we say hello, and then it knows that it should ignore these. So now if you run this, then this worked again, and it filled the hello with not a number. And you could also specify what it should use instead. So here we can use the argument filling values equals, and so you might want to set this to 0, but so in this example, so just that we can see it, I will set this to 9999 and as a float. And for the pandas function, what we can then do after loading is to call data frame and then set data frame fill NA, not a number, to 9999.0. And now if we run this, then we see that here it replaced the not a number with 9999. And here I have to say, of course, data frame equals this new data frame. And now if I run this again, then we see that it worked too for the pandas method. So this is how we can deal with missing numbers. So usually you want to say this to 0, and then you should be good to go, because a lot of errors that beginners see is because there are missing numbers, and then your algorithm crashes because it doesn't know how to deal with this. So always make sure that you deal with missing numbers. Then I recommend to specify the data type, and now you should also know how to deal with headers. And yeah, so these are the preferred two methods that you should know: the NumPy gen from text method and the pandas read CSV method. So yeah, that's all you need, and I hope you enjoyed this tutorial. If you like this, please subscribe to the channel and see you next time. Bye.